Welcome to this session of POPL. The first talk we have today is ReSharp, high-performance derivative-based regex matching with intersection, complement, and restricted lookaround. Was it correct? All right, so Ian is presenting. Stage is yours.
Right, thank you. So my name is Ian. I will be presenting ReSharp, high-performance derivative-based regex matching with intersection, complement, and restricted lookarounds. This is joint work with Microsoft Research and my co-authors Margus Vanes and Johan Ernitz. So we are presenting a matching algorithm, and there are four main highlights about this algorithm, which are separation of concerns, our approach to lookarounds, the simplifications that we do, and the resulting performance that we get from this approach. And I will leave out some of the complex theory, but I will first cover span semantics for matches, and then a large part of the talk will be introducing you to intersection and complement in regular expressions, since they're not part of any industrial regular expressions today. So, and then I will explain what makes this possible and how we can make this fast. So the problem that we are solving is finding match spans. So for example, we have this regular expression right here, which finds all instances of ABC located at the start of a line. So for example, if we have an input such as this, then the matches, there's one match at the very beginning, which is ABC at the start of a line. And this returns us these positions where the positions themselves are located between the characters. So the first position is at the very beginning of the string before A, and it ends after C. And I also want to make the distinction between just language membership, so just the match contents, and the match surroundings. So context assertions they have a lot of significance when you're looking for substrings in an input. So yeah, and what makes our approach to this different is that we have separation of concerns. So we get separation of concerns by having the intersection operator. So for example, we can define, we use underscore star to represent the set of all strings. And for example, we can constrain that we can match anything that starts at the start of a line. And then we can, for example, say that we're looking for ABC, and we can use this intersection operator right here to combine these two constraints. And the intersection operator itself is located in the bottom right here. And we can use this intersection operator with both these context constraints and the match body itself. So we can specify requirements in these small incremental steps. So this gives you some idea of what you can express using this language. Next, let me work you through an example to show you what exactly I mean by this. So for example, we have this piece of text right here, and we want to extract the names of the authors from this text. And we can do so by describing properties about each of these matches. So for example, all of these matches are located after the word author on the same line. So this gives us this one long match that is located right there. And all of the subsequent constraints that we add apply to this area of text. So we can also say that, for example, none of the matches must contain and, which splits the matches into three. So now we have three matches right here, which we can combine with this intersection operator right here. We can also say how each match must begin. So we can say that every single one of the matches starts with an uppercase character, which fixes the beginnings right here. And we can also say that all of the matches end in a certain way. So for example, here, all of the matches must be followed by an and or a closing brace. So this is not the constraint on the match itself, but its surroundings. And combining these four constraints together, this is precisely the pattern that matches all of these substrings in this input. So this is one set of possible constraints we could describe to extract these matches. And what I want to emphasize around here is that the meaning of each constraint is preserved. So it still has the exact same meaning no matter how many other intersections you add here. And semantically, we return the leftmost longest non-overlapping spans that satisfy all these conditions. So for example, we could also return just Owens, but this is not the leftmost match. So we return Scott Owens. Right. And there's also a nice correspondence between this form version. So we could fill in some forms and we could neatly translate this into a regular expression. So you don't really need to know regular expressions to use this. Right? So it still works exactly as you would expect, but the highlight here is that we have some new non-standard search options available. Right? And once we describe these constraints, then we can lazily compile this into a program, which can find these substrings very fast. So the highlight here is that, for example, this query can be compiled into a program that runs in O of n time and solves all of these constraints in parallel with one pass over the input string. So it finds all the valid match beginnings in just one pass over the string. So this gives you a very high level of performance. And the way we do this is using the derivatives. So for example, if we are looking for a line that contains A, B, and C, and then we find the C, then we're still looking for A and B. Right? So this is the derivative with respect to C. And this gives us, so each state in this graph has this label that is another regular expression. Right. Next, I'll talk about algorithmic complexity. So the complexity of solving this problem usually consists of two parameters. So there's the length of the string and the size of the pattern. And ReSharp is a lazy DFA engine, which means that we do as much work as we can at the very beginning, and we compile the pattern away so that the runtime itself is as fast as it can be. So we compile this into a graph. And why it's O of n times n is because we only construct the states that we actually visit. So we construct each state lazily as we get there. And the main highlight here is that a DFA engine's runtime does not depend on the size of the pattern at all. So anything you can compile runs very fast. But this compilation time, of course, can be very expensive. That's the drawback. So here are some more examples of how these derivatives work. So for example, if we are trying to find a pattern that's anything except ABC, and this is how the graph would look like if we visited all the states. So one of the main insights of how complement works here is that we can construct it incrementally through derivatives. So if we're looking for anything that is not ABC, then we can lazily construct these derivatives. And this is the only state that does not have a green border, for example. So this is the only non-matching string. So the complement of ABC matches everything except precisely ABC. And on the right here, there's the line that contains A, B, and C, where we would construct a graph like this, where each state represents the constraints that have not yet been satisfied. So if we're looking for a line that contains A, B, and C, and we have found the C, then we are left with A and B. And if we find a B, then we're just left with A, and so on. Right? We also have a different approach to lookarounds, which we just compile directly into the graph. So since we can construct all of these states lazily, then we can also compile these context conditions into the graph. So for example, if we're looking for AB that is followed by C, D, E, F, then what we do is that we just start incrementing a counter once we get to the context part. And then we can just point to where the match really ended. So this is how we can encode these offsets into the position. And this is only possible because we can create these states lazily, because this can be infinite. If the context length is infinite, then it can grow to a very large state. But in practice, you only construct the states that you actually visit. Right? And then we do a lot of simplifications. So we have a lot of simplifications in the paper, and the most basic ones are just simple Boolean logic. So for example, the complement of all strings is no strings, right? And this is on the language level, right? So you can think of this as Boolean logic on the language level. So the not false is true, The double complement is just the match itself. And if something is always true, or something else, it's still always true. And if you constrain something by the set of all strings, then it doesn't really constrain anything at all, so you just can remove it, right? And right, and to have this Boolean logic in the first place, you need to have a commutative OR. So we do leftmost longest matching, and we do this for a reason. Because if you're doing leftmost longest matching, then the order of OR does not matter. But almost all industrial regular expression engines work like this on the right, where order matters. So the way this works is that you try the one on the left, and if this fails, then you try the one on the right, which gives you this very different kind of semantics. And I really want to emphasize this Y over here, because it's not just an arbitrary choice. It's not just a preference, but it also has a lot of significance when you're matching regular expressions without complement or intersection. So for example, let's say you're matching this regular expression right here. So you're matching up to 8 characters followed by A, or up to 9 characters followed by A, or up to 10 characters followed by A. And you can just simplify that to be the longest out of this, because the language of this contains all the other opportunities as well, right? But if you're using PCRE matching, so leftmost greedy semantics, then you're not matching neither the shortest nor the longest in this list of alternatives. So if you fail matching this, then you try this. So it has a different kind of semantics, right? So if you were to reorder these, this would actually change behavior. And also, for example, if you have 2 alternatives and they end in the same way, then we can group them together if you have leftmost longest semantics. But if you would do the same with leftmost greedy semantics, then you would change behavior. So you would get different results when you're actually matching. So the highlight here is that using leftmost longest semantics gives us smaller DFA representations than leftmost greedy engines. And we take advantage of this during matching. So there are a lot of simplifications. I will not go through them, but the highlight here is that a lot of them are just not applicable to leftmost greedy engines. In particular, this one, for example. So if 2 patterns end in the same way, you cannot group them. And this leads us to performance, where there are 2 main highlights, which is that this is a logarithmic chart, and we're positioned all the way to the left here. Right, so when you get up here, that's a 10,000 times speed difference. And if you look to the right here, that's a 10 to the 5th. That's a 100,000 time difference, right? So the highlight here is that all of the engines right of this position right here use PCRE semantics. So only Hyperscan gives you the shortest matches, and ReSharp gives you the longest matches. The rest use PCRE semantics. So for example, if you have a lot of words, so you have a large dictionary of words, then this gives us a very big performance benefit compared to the others. So Hyperscan right here does not support 2 of the benchmarks, because Hyperscan is somewhat restricted, and it has different semantics, but it also has very good performance on these large examples. So I showed you some extreme examples, but also in average cases. So in average, over the set of benchmarks that we tried, in terms of geometric mean, we're over 71% faster than the next engine. So we have very good results on average as well. Right. So in conclusion, we have this separation of concerns. So we can describe properties about matches and actually get these results in this nice, intuitive and composable way. We have these automata lookarounds where we can compile these into the graph itself, hoping it runs faster once it's actually compiled. And we do a lot of simplifications, which we do. Many of these we can do because of having leftmost longest semantics. So maybe one more key reason why we use leftmost longest semantics is because this actually gives intersection and complement meaning. Because under non-commutative OR, having this Boolean logic is quite difficult. And this gives us very good results at the end. So this is all the slides. So questions? There.
All right. Two questions. When you were talking about the performance, you had a slide where compile time and runtime performance.
Yeah, right.
And you said that the compile time performance was dependent on the length of the input string, and I couldn't really understand that. How do you know the length of the input string when you're compiling the regular expression?
Right, so if you're compiling the regular expression lazily, then you can at most create one state per character. So you reach a state that you have not constructed before. So for the entire string, you can at most create one state per character. That's where the n comes from.
So if I have some code and I compile a regular expression, and then later in the code I run that regular expression,
then it could start compiling lazily, yes. So.
Oh, okay, so compilation time could be included in the execution time of my program.
Yes, yes.
Gotcha.
So you can do it ahead of time, but this has a drawback, of course, and you can do it during matching. But the idea is that the throughput would be good. So any subsequent inputs that you use would reuse these same states that you have created for the first one.
As long as the new string is of shorter length? Or if you're streaming
so
the input?
Any state you reach, if you have already created, if you have already somehow reached this position, then if it's created, it will not be constructed again. So,
okay.
So you reuse the compilation time for subsequent strings.
Okay. And then can you comment on memory usage of your approach versus the other ones you looked at?
I have not measured that, but well, we wanted to point out this, right? So here, you cannot group them together, so it should be large, but I have actually not measured that.
Okay, thank you.
Thank you for the nice talk. I was wondering, could you speculate on why PCIe chose those semantics? Like, I mean, you made it sound like it's terrible in every regard. Does it have any advantages?
It does have some advantages. So it has a lot of these convenience features that people are used to, and it has been this way for a very long time. But really, the reason why PCIe is the standard is because of the backtracking algorithm. So all of the engines that have PCIe semantics are imitating the same behavior. So you would have the same match results as you would expect from the old ones. But you can do some things. So you can do some things that you would not do in leftmost longest matching. So for example, the lazy loops, I think, or is it the shortest loop? So if you have if you're trying to match as little as possible in a clean E star, then you could add that. And there's also back references and things like that that are very easy to add if you already have these semantics.
Okay, thanks.
I understand how you get order in complexity when you're matching a single pattern. Mm-hmm. But I didn't understand how you keep it as in complexity when you're matching multiple patterns simultaneously. Do the patterns need to be non-overlapping?
So, for example, in the case of an intersection, you mean? Okay, so looking at this graph right here, you only traverse the states that you. So you do at most one state transition per character of input. So the complexity goes into the graph, but you will still do just one transition per character at the very worst case. Multiple strings. You mean return all the results? Okay, yes. Removing overlap between these is not often. So you can find all the beginnings of the overlapping strings, but removing overlap is not often.
Maybe a quick one, and if the next speaker can already prepare.
Hi, this is really nice work. Mm-hmm. So historically, people have avoided intersection because there's a kind of product automata state space explosion. Mm-hmm. Okay, sorry. This is really nice work. Historically, people have avoided intersection because there's a product automata in the state space explosion. Can you maybe say, if I'm using your engine to match several strings, like how you avoid running out of memory? Like, is there anything that really helps?
There is only a limit to how many states you can create. So if you create too many states, our way of preventing that is just to throwing an exception. That's all.
Okay, thanks.
All right, thanks again. And then the next talk of the session is Pantograph, a fluid and typed structure editor. Jakob is giving the talk. Is it? And the stage is yours.
All right, hello, I'm Jacob, and I'm going to present
Hello? Awesome.
Okay, thank you. All right, hello, I'm Jacob, and I'm going to present Pantograph, which is a fluid and typed structure editor. This is joint work with Henry Blanchett and my advisor, Leo. And in a minute, I'll get to what I mean by fluid and typed. But first, let me talk about structure editors. So here's you programming in a text editor. There's the programmer on the left. You're writing a text file that says 4+5. Guess it's a very ambitious piece of software that you're working on. And in a text editor, that text file is parsed into a syntax tree, and then that syntax tree is typed to produce an annotated typing derivation. So you're familiar with this pipeline in a text editor. But in a structure editor, on the other hand, we have no need for a text file. There's no text file. And instead, the programmer directly writes the syntax tree. Now, in many structure editors, the programmer is writing an untyped syntax tree, which is still then type checked to produce a typing derivation. But in some structure editors, like Pantograph, the programmer is directly writing a typing derivation. So in Pantograph, there's no intermediate representations for the program at all. There's no text. There's not even an untyped syntax tree. So what does this look like? What does it look like to directly edit a typing derivation? Well, let me show you a basic structure editing setup. So here's a blank program in Pantograph. Here we have a hole of an unknown type. And what you can do with the hole is you can fill it in with an expression. So for example, I could put a plus expression into the hole. And now I'm left with two new expressions of the type int, which are the children of the plus expression. And for example, now I could fill these numbers 4 and 5 into the holes. And another thing I can do is I can wrap an expression around an existing one. So for example, I could put this if expression around the 4+5. And one final thing you can do in this basic structure editing setup is you can cut and paste entire terms. So for example, I could move the 4+5 to the other branch of the if. So what I've just shown you is a very traditional plan for a structure editor. To recap, you have these typed holes that represent unfinished parts of the program. You can fill expressions of the correct type into the holes, and then you can move entire terms around. And this is nothing new. This idea has been around for decades in various forms. There are some basic advantages of this approach. We'll get to some more interesting advantages later, but there's no compile time errors, right? There's no parser, so you can't have a parse error, and there's no type checker, so you can't have a type checking error, right? The programs are just directly correct by construction. But there's a well-known flaw with this basic structure editing setup, which is how do we edit existing code, right? Filling in typed holes is all well and good as long as you never make a mistake, but what if you have to actually go back and edit something? So for a minute, I'm going to be using this example. We have these two little function definitions, double and square of the type int to int, and then the call at the bottom, double the square root of 10. So for example, suppose that I want to swap the order of these two definitions, or maybe I want to swap the order of these two function calls. Well, to do this in this basic structure editing setup, first of all, I need a hole to do anything. And then it's actually going to take 4 cut and paste operations to do this. So there's the first one, there's the second one, there's the third one, and here's the fourth one. So it's a very clunky interface to do a basic thing like this. And even worse, what if I want to make an edit that actually changes the types of something in the program? So for example, maybe I want to add an argument to this double function. Well, if I'm allowed to add this lambda here, then the program is no longer well typed. So this seems to conflict with the idea that we're editing a typing derivation directly. So the challenge that we set for ourselves for this project is, can we make a structure editor in which the programmer is directly editing a typing derivation, but yet we can still freely or fluidly edit the program, edit existing code. And there's other approaches you could take, like Hazel adds another kind of intermediate representation, but this is the idea that we're pursuing. So to solve this problem, Pantograph introduces two ideas. The first is tree selection, which will help us to rearrange things in our program more easily. And the second is an automatic type refactoring system in which each edit will have a typed meaning. So here's this double square thing again. And in a tree editor, the cursor goes on expressions. So we could put the cursor on these let expressions or on these function calls. And we've seen how it's very difficult to rearrange things by just moving entire expressions. But by contrast, in a text editor, it's very easy to rearrange things. So what does a text editor have that a tree editor doesn't? Well, in a text editor, we have a cursor, which goes in between characters in the string. And we've just seen that in a tree editor, the cursor goes on expressions or on nodes of the tree. But in a text editor, there's a second thing called a selection, which goes in between two possible cursor positions. So the idea that we had is, let's extend this by analogy to a tree editor. And so a cursor in a tree, or a selection in a tree editor should go between two possible cursor positions. In other words, it goes between two expressions. And specifically, the tree selection is the area inside of one expression and outside of another expression, known in PL as a one-hole context. So let's look at how we can use these tree selections to actually rearrange things in the program. So for example, I can make this selection by clicking and dragging from one expression to another. There I've selected the area inside of the double function call, but outside of the square function call. I can then cut that, which puts it in my clipboard and removes it from the program. And then I can place my cursor on the 10 and paste it, and now I've rearranged those two function calls. Similarly, I can use the same principle to rearrange these two let definitions. So I've made this selection, the area inside of the first let expression, but outside of the second one. I can cut that, and then I can paste it on this expression at the bottom, and now I've rearranged my function definitions. So it turns out that this concept of tree selection corresponds to quite a lot of common program edits. So let me show you some of them. So we've just seen the one about reordering function calls, and this is that again, but in this case, the function call that we're moving has two arguments, and the inside of the selections in the middle. So this is just to show that there are tree selections that don't correspond to text selections, right? This takes two steps in a text editor. We can also use a tree selection to rearrange function arguments. So in this case, these are curried applications. The tree selections actually work nicely with curried applications. You could also use a tree selection to reassociate binary operators. This is actually the same thing again as just reordering the function calls, right? So in a text editor, this would be different, but on the tree structure, this is the same operation. And one last one, on cons lists, these tree selections end up corresponding to just selecting a sublist, right? So they correspond to just usual list selections, and then we can use the tree selections to reorder things in the list. So I've shown how we can use these tree selections to more easily rearrange expressions in the program. But remember, there was this other problem of what if we want to make an edit that actually changes the types of things? So here we wanted to add an argument to this double function. And let's just go ahead and see what happens when we actually do that in Pantograph. So I can place my cursor on this expression, and I can add the lambda. And what's happened is that Pantograph has automatically changed some stuff in the program in response. So I just added the lambda in green. Pantograph automatically added this argument to the annotation at the top, and it also automatically added the whole argument at the call site at the bottom. So this might be familiar if you've ever used like an IDE or a language server where there's some feature where you like right-click on a function, add argument. It might do something like this. But in Pantograph, actually every single edit is a typed refactoring. So let me show how this works on a higher order function. So for example, here's a map function. It inputs this parameter f of the type bool to bool, and then it's taking a list of bools, outputting a list of bools, and at the bottom, I'm mapping the function not over this list. So suppose that I want to add a higher order parameter to f. Maybe I'm turning this into map with index or something. So let's do that in Pantograph. So I can add this argument here in the annotation. And again, Pantograph automatically added some stuff. It changed the annotation at the top, and it added the argument to f. But here, the not at the bottom, which used to be of the correct type bool to bool, it's actually wrapped a lambda around the not to fix the type of that. So let's take a look at how this type refactoring system actually works. And to do that, I'm going to use essentially the simplest possible example, which is this very small program, lambda x.x applied to 10. The programmer here is inserting a lambda around the 10, and then Pantograph will respond by adding an argument at the call to the x. So to represent the way that the types of things change, Pantograph uses what we call diffs, like diffs from version control. So that this 10 expression, it used to have the type int, and now lambda wide at 10 has the type int to int. So the diff plus int to int expresses that we've changed the type by adding this int arrow to it. And what Pantograph does is it will propagate these diffs through the program step by step to make the edit. So this is the starting point, is that we're at this expression, we've just changed the red expression, and we know that we need to change it according to this diff plus int to int. So this is on the right-hand side of an application. So the next thing we need to do is we need to change the type of the function on the left of the application. And so we need to change the input type of this function. And so this function needs to change by this new diff plus int to int to int, which reflects the fact that it's the input changing. And since this expression is a lambda, to change the input type of the lambda, it needs to change the type of that variable in the body of the lambda expression. And then finally, it adds the argument to x. So I've just given one example of how this typed refactoring system works. I won't go into too much more detail in this talk. But in the paper, there's some more math. Basically, we define these diffs form a category. They can be composed and stuff. We have this small step system for propagating the diffs through the program. We prove all the standard kinds of theorems about that, like type preservation and confluence. And just one thing about this that I think is interesting is that the workings of the system are in large part automatically derived from the typing rules of the language. So for example, here's the typing rule for a lambda, and the way that it just knew to change the variable in the lambda is actually derived from this typing rule in the implementation. So that's enough about the math, but back to it a little bit of a higher level. I said at the beginning that the goal was to operate on this well-typed typing derivation. So does our system actually always do that? Well, not exactly. So there are some cases where it will need to actually insert an error into the program in order to deal with something. So here's this map function again. And suppose that I want to change the output type of this f parameter. So I'm going to go ahead and change the output type of this from bool to int. And what you can see is that Pantograph has added this, what we call a type error boundary in the program, where there's this discrepancy in the types. It couldn't resolve this by like adding an argument or something. And in a way, this is a lot like what a type checker does, in that it's placing a type error. But it's also different than a type checker in some interesting ways. So first of all, these type error boundaries are actually first-class terms in the program. And what that means is that I can select it with a tree selection. So there I've selected the area inside of the error, but outside of the call to f. And then a second, what I'm going to do is I'm going to delete this type error boundary. Right? Wouldn't that be nice? You have a type error in your program. You just delete the error. But let's think about what's going to happen is that in Pantograph, when you delete a selection, you're telling it that the type inside is the correct type that you want, and it should make the program around that conform to it. So currently, map outputs this type list bool. And when I hit backspace and I delete this selection, it's now changed it to list of int to correspond to that. So let me just show one more example of how this typed refactoring system can place errors but still do something a little bit different than what a type checker does. So here we have this program, this f with 3 integer inputs, and then we have it applied f of 1, 2, 3. And suppose that the programmer wants to delete the second of these 3 arguments. So Pantograph describes this internally with a diff. Again, here it's a minus diff, int to minus int to bool. And it's going to respond by placing this other kind of error form around the second argument there. But actually, what you'll notice is that a type checker wouldn't be able to know which of the arguments to place the error on, because all that it would know is that f takes 2 integers now, and it's applied to 3 at the call site. Even if it knew that it used to take 3 integers, that's still right. So the fact that this typed refactoring system actually acts on the edit itself gives it access to more information than what a type checker has. So at the beginning, I said our goal was to make a structure editor where you're directly editing a typing derivation, but yet you can fluidly edit programs. System is not perfect. There's certainly edge cases that don't work so well. But overall, we believe that we've demonstrated that this is possible with these 2 things, tree selection and this automatic typed refactoring system where every edit has a typed meaning. We also ran a user study in which we got 15 or so undergrads. We trained them how to use Pantograph. Some of them learned how to use Pantograph very well. Some of them were completely baffled by it, had no clue what was going on. Overall, the text editor was a little bit faster. But we did, in making this user study, we made a tutorial to teach people Pantograph. So if you go to the paper and you click on this link, it takes you to this tutorial. And it goes through it from the beginning. It explains selections. It has a bunch of different exercises. And it's entirely self-contained. So if you want to try out Pantograph, you can find it in the paper. Thank you.
Thanks. How do you handle comments?
It doesn't have comments implemented, but if I were to implement it, it would probably be a form that wraps an expression and then also has a string where you can type the comment, is probably how I would do it.
Hi, thanks. So in this example you showed earlier, when you were reordering these two functions, there was a moment when there was no double function,
Yeah.
but the program called double.
Yeah.
And you didn't talk about it, but it turned red. Like, I guess the
Yeah.
editor was doing something. Could you say a bit more about what's happening there? And
Yeah, so there's
how
a
that's a valid program.
Right. So as I said, the goal in general is to try to maintain well-typedness, but there's some situations where it doesn't do that, and there's a few different forms that it puts in the program. So I talked about the type error boundaries in a little more detail. There's this one where it just can have a variable that's been unbound, and then when you repaste the binder, it reattaches it, and then internally it has a De Bruijn index again. So yeah, we would sort of like to unify these different concepts of errors, but they're just different things in Pantograph.
This is really cool. I noticed that most of your all of your examples were simply typed, and I was wondering, have you tried this out on any sort of polymorphic calculus?
What Pantograph does have is it has some built-in functions that are polymorphic. So actually, the example with map, cons is polymorphic, for example, and when we change the type of the list from bool to int, it actually makes use of that. But Pantograph does not have user-defined polymorphic functions. So yeah, that's something still to do. Yeah.
Hi, I had a question about your empirical study. So you said you compared to a normal text editor, and I'm wondering, did you compare to something like Emacs or like a modal text editor or both?
So what text editor we used in the user study?
Yeah.
Yeah, so we made a thing in a browser that used it had like some of the basic features like, red underlined errors and stuff like that. But it was just a custom thing that we made for the user study.
Okay, but did you compare it all to like modal editing in Vim?
Oh, no, we didn't compare it to Vim.
Okay.
Although that would probably require also teaching the participants how to use Vim. But, yeah.
Possibly.
Yeah.
I mean, in my experience with synthesizer generator and all things, like text editors are just, so superior to structured editing, and structured editing just slows you down. But there's Blockly, right? So have you considered sort of drag and drop and sort of, there's a huge amount of use of trees, in these visual languages where kids start to learn about tree structure and programs. So anyway, I think there's an opportunity there. I'm pretty pessimistic, as you can tell, about it for text. And maybe we'll get there. But thank you. Very good. Very cool stuff. So there's not really a question.
There's no question. All right.
Right, Neil.
I have a question. Are there modules, or does type changes propagate through other files or something like that?
Yeah, in Pantograph, it's just a single expression is what's implemented. But
I see.
That would definitely be something to think about.
Hi, this is really nice work. So first I want to say I'm especially excited about this for type systems that are really hard, like dependent types. And second, one thing I didn't quite understand in your presentation is do you have sort of multi-selections? If you have a list of integers and you change the first element to a string, you might want to select a whole bunch of things at once.
I'm not quite sure what that means. Yeah, you have a list of integers, but you change the first one to a string.
Yeah, now it's a type incorrect list. So the change you might want to make might be to apply a function to all the elements in the list.
Okay, so if you had a list with a bunch of integers and you changed that, so that wouldn't be a selection, but yes, you could edit the type of it to turn the first one into a string. What that would do is it would place a type boundary around all of the other elements because they would be expected to be strings now. Yeah.
Hey, thanks for a great talk. The question I had was, sometimes when you make a change, right, and you propagate this through the tree, you seem to have multiple options for what you could do. So in the example that you showed where you added the lambda, right, you could have also just changed the type of the outer thing to be a function instead of adding the argument to the inner thing. How do you make those decisions? Do you have any sort of model for how to decide this? or is this just the closest
Yeah,
thing in
so
the
I
tree?
mean, there's a deterministic algorithm, and we've shown it's confluent, so it does a predictable thing. And like, if you learn how to use pantograph well enough, you definitely can understand what it's going to do. So one side is like, you have to get used to it as the user. But then, yes, there are also situations where it feels like maybe I wanted to do this other thing, and then I have to take some longer sequence to get there. So that could be a problem with this kind of approach, yeah. Absolutely.
So we need to move to the next talk. Maybe you can take the next questions on offline. Let's thank Jakob again. Then the next talk is Grove, a bidirectionally typed collaborative structure editor calculus, and Cyrus is presenting.
Okay, is this on? Yeah, okay. Cool, hi everyone. So there's a lot to unpack in the title of this paper, but the central thing is the central word there, collaborative. So programming is collaborative. You always start with an obvious statement in a talk like this, right? I mean, you know, we use a lot of different tools to collaborate with one another on software. Perhaps central to that are version control systems. I'm going to use Git in our examples. There are many others, Darks and others, that are very interesting. And then there's kind of these social coding platforms like GitHub and GitLab that are built on top of that. Some of you might also use collaborative editors, so think like Google Docs but for code. So there's like Visual Studio Code Live Share and other tools like that. So I'm going to mostly focus on the version control in terms of terminology and examples, but for the purposes of kind of this talk, a collaborative editor like this is just a really fast, kind of fine-grained version control system. Right? You're propagating the changes continuously rather than in batches of commits. So we're at POPL, so why is this a programming languages problem? Well, central to these tools like Git is a programming language. You've probably seen the patch language, the Unix patch language. Fun fact, who knows who invented the patch language? Nobody? Larry Wall, yeah, of Perl fame, the second most popular programming language. So the patch language is a very simple language. It's kind of like a little imperative language on how to edit a file to change it into another file, right? So it is a programming language, but of course you could be forgiven for not knowing the inventor because we don't generally write programs in this language ourselves, right? Patches are synthesized, if you will, from the file system state, from two different versions of a file. So you use diff, which is a program that generates patches from two different states. And then, so the kind of central way in which we collaborate with one another is by sharing patches with one another through version control systems like Git. So let me just set up a really simple example to set up some of the problems with these current systems. So let's say you have this like 2-line file, and Alice and Bob are both editing this file separately. So Alice renames this function f to append, and Bob adds an argument and does something with that argument. And so you can see what the generated patches would look like there. And then let's say Bob shares his patch with Alice. Well, then you need a merging algorithm, right? You have to do a merge. And so the merging algorithm that's typically used is what's called a 3-way merge algorithm, where you actually take all 3 of these things, the base branch and the 2 patches, and you try to merge them together. So what's going to happen when we merge this? So the answer is a merge conflict. And this seems like just part of the water in our programming ecosystem, that these kinds of things are going to happen here. So in particular, that line that starts with a def was modified by both Alice and Bob, and so there's a conflict there. But because it's a 3-way merge, the base branch and Alice's branch don't diverge on that return line, and so Bob's change is not conflicted there on the last line. Now, I would say that this is already a problem because of a sort of a granularity issue, right? These patch languages operate at the level of lines. Kind of morally, right, the change that Alice made to rename this function is independent of the change that Bob made to add an argument. So it would be nice if this wasn't a conflict, but it is a conflict. But let me give you a kind of more pernicious example that could actually cause real problems that you might not immediately detect. So let's say it's the same setup. Alice and Bob are both making the same edits to this function, but also they both have different views on where in the code base that these functions should go. So they both relocate these files to different locations. I'll call them new location 1 and new location 2. So from the perspective of patch synthesis, what happens here is, well, it looks like a deletion of the original function and an insertion of the new version of the function in both of those locations. So given these two patches, what happens when we do our three-way merge? It works and the code is duplicated. There's no merge conflict, despite the fact that we had the same edits as before and one more conflicting decision was made about where the code should go. So why is that? Well, the version control system didn't see the actual edits. The programmer's actual edits were lost, and so you have to use heuristics. These patch synthesis systems like diff, as wonderful as they are, right? They are heuristic systems that have to infer what must have happened in the editors that you were using from changes to the file system state. And code relocation, especially when that's like independently, but also especially when that's combined with edits to the code, it's just impossible to tell whether that function f and that function append were from the same place because they have changed so much, right? And these systems often have like heuristics. If it's changed a certain percentage, it's treated as a relocation. It's like very brittle and messy. So this is, I would say, fundamentally problematic. So what is the solution? Well, what we can do is we can just eliminate patch synthesis entirely. So I'm going to talk about version control without diff. How do we do that? Well, we just saw a great talk about structure editing, right? So what if we could actually record the edits that the programmers performed, including the code relocations, and then share those patches that were derived directly from our actions rather than inferred heuristically from file system changes? So we're going to do this in the setting of structure editing. I think actually there's parts of this talk that could go into plain text editing as well. But to also solve that granularity problem that I talked about earlier, structure editing is a really nice platform and also work that my group does. So we already saw a talk about structure editing, but just briefly, what is a structure editor? It's an editor that at its heart has another programming language, which is actually kind of going to align with this patch language idea, this edit action language. This is a language that directly transforms program structures. You can think of these as syntax trees with holes, or in synthesis, it's called a program sketch. So there are lots of interesting examples of structure editors in use today. In my freshman class that I'm teaching this semester, I did a show of hands to see how many people learned programming with Scratch, and it was like half the class. So lots of people are learning how to code in Scratch and Snap and other tools like this, these block editors. We just saw Pantograph, really cool structure editor that has some interesting type-directed features. There's a mention of Hazel, which is the tool that we are building, the structure editor that we're building in my group. This talk isn't specifically about Hazel. The ideas apply generally, so I'm not going to give you a Hazel demo or anything, but ask me for a demo. I think if you're the kind of person that sort of like looked at structure editors in the 80s and 90s and decided they're not usable, I think we have arrived at a new point in that design space. So I'm happy to give you a demo and convince you that actually they are usable now. And Tyler is the system that we are developing to generate structure editors from grammars for JavaScript and other languages. So expect to use a structure editor in the next decade, I would say. There's lots of other cool examples. JetBrains has MPS, there's Lambda, there's lots of others out there. So if you allow yourself to use a structure editor, then you can derive patches directly from structure edits. Oh, sorry, that's a video. So what about merging, okay? So that's really like we can share the edits, but how do we merge edits together? So the usual approach in both kind of version control systems and kind of real-time collaborative editors is to define an operational transform. So the three-way merge algorithm, this is kind of underappreciated, is an operational transform. The idea is for every pair of actions that might be kind of sequenced in a change, you have to define a transformation of the second action to make sure that the order doesn't matter anymore. So you could do things like shift the indices of like line numbers and column numbers and things in the second one so that they're shifted by the appropriate number of insertions that happened in the first one. So this is fine, and there's lots of interesting work on operational transforms for various kinds of data structures, but it's very involved, it's very specific to the action language of each editor, and it's very brittle. Every time you make a change, you have to like prove all the properties about the convergence. So I'm gonna do something, so I already said I'm gonna get rid of diff. I'm also gonna get rid of merge. Instead, what I'm gonna do is I'm gonna define an action language where there is no need for a operational transform because all of the actions commute without transformation. You just literally share your edits with one another and play them in any order, and you converge on the same state. Okay, so that seems interesting. So the underlying ideas have been explored in the systems community, the distributed systems community, under the rubric of CRDTs or CMRDTs. This stands for commutative replicated data type. So the idea of a data structure where all operations commute is very old. The systems community kind of discovered that this is really useful for distributed systems in the 2011 or so. So classic examples are one-phase sets. So a set where you can only insert naturally commutes. You can only do insertions. An order doesn't matter. There's two-phase sets where you can also do deletion of things, but deletion is permanent. So there's this idea of a tombstone where something is permanently killed off once it's deleted from the set. So that also is commutative. So there's lots of other examples. So we're going to define a CMRDT. Okay. So if our editor state were a CMRDT, like I said, merging would reduce to applying remote actions directly without transformation. But this is easier said than done. Like typical structure editing actions don't commute by default, right? We had a paper at POPL 2017 on a structure editor calculus. By no means do those edits commute. So how do we make them commute? Well, what we've done in this paper is we've defined Grove, or the Grove patch language, which is what you can think of as sort of an intermediate representation in IR that structure editor action languages can translate down to. And it's a very simple language that provides this commutativity property. And I'll detail it in a few slides. But I just want to note there has been some prior work on tree CMRDTs. But there's a couple of things specific in the coding space that we want to make sure we support that prior work hasn't supported. So one is that sometimes you get commutativity by resolving conflicts kind of arbitrarily and consistently. That's not what we want to do. We want to explicitly represent conflicts so that the humans involved can mediate conflict resolution. And then a lot of these systems don't have support for relocation, which we think is really central to actually represent that explicitly rather than just insertion and deletion. So the Grove patch language resolves these issues. And kind of the key insight is that although we are working with trees, syntax trees, we have to kind of project this into a larger space of label-directed multigraphs. So we're developing a CMRDT for label-directed multigraphs. But then we'll get back to a collection of trees, which we'll call a grove, that contain explicitly represented conflicts in addition to wholes. And these things have to be linked with one another. So it's a collection of trees for a reason that I'll show you in a bit. OK, so let's do some examples here. OK, so actually, this would be a lot easier if I could point on my screen. No, not like that. Sorry. Okay, I'll have to look this way. Okay, so like I said, the central idea is to represent our program state. I'm just going to use simple expression language with just arithmetic for our examples here, but this generalizes. So we represent our state as a graph. We have a special root node. That's the dot there. So each node has a kind of a constructor for that AST node. And then we have unique IDs on all the nodes as well. So that's unique ID 0, 2, and 4 there. And then you have edges between them, and the edges are labeled by a position. So the root node has one position, root. The times node has a left position and a right position. In this case, there is an X on the left, so that's labeled with L. And the edges also have unique IDs. And then there's no right node here, and so when you decompose this graph into a tree, you leave a hole in that position. So there's no edges there. Okay, so that's kind of our starting state. Simple edits kind of behave as you would expect. If I want to fill that hole Y, that hole with Y, I create a new edge and a new vertex. Technically what happens is when you create an edge, it mentions a vertex, and that vertex becomes created when it's mentioned by an edge for the first time. So it's really edge insertion and deletion is the core of this Grove patch language. So we've created our Y. deletion is also edge deletion. Notice that the node, the vertex x, is not deleted. It's just the edge that's deleted. And this is really critical to the whole thing, is edges are the thing that are being edited. Vertices, when they come to life, they live forever. Okay, so one way to think about it in terms of CMRDTs is that vertices are one-phase sets and edges are two-phase sets, because edge. Okay, so some kind of user-facing edit actions correspond to a sequence of multiple kind of patch actions. So if you want to wrap the times node from the last state here with a plus node, that amounts to temporarily disconnecting the times node, creating the plus node, and then reconnecting the times node. That would be kind of atomic from the perspective of a user, but in the patch language, that's multiple steps. And then code relocation is also just sort of edge deletion and insertion at the new location. So nothing actually gets, no vertices that get deleted. It's just that the previous location of the times on the left here gets relocated by deleting the left edge and replacing it with a right edge from that parent or from whatever the new parent is. Okay? So that's just kind of the single user perspective. Now let's talk about collaborative structure editing in Grove. So the diagram that we're going to use here, so this kind of a legend for what you'll see in the following slides is Alice's edits are in red, Bob's edits are in green. You'll kind of see them. And then the squiggly blue line is the convergent state that arises when they share their edits with one another. Okay? So at the bottom there, you see the key theorem, which is this commutativity theorem that says, for all graphs G and G prime and all graph patch commands pi1 and pi2, a graph patch command is literally just add or delete and then an edge ID, or an edge. If you do this kind of editing transition in one order, it's the same as doing it in the other order. So a very simple commutativity theorem. Okay? So let's do a couple more examples. So in this example, we start from the previous state, and what Alice does is she fills the hole in the multiplication with u here. Bob does something independent of Alice, but in the same expression, sort of on the same line, renames y to v. Those edits get shared in terms of the edge insertions and deletions, and they kind of don't interfere with one another. There's no conflicts, and so everything merges cleanly, and they go on with their day. So that solves this granularity problem. This is just a single expression, but it doesn't matter. There's no notion of a line in this system at all. Okay, another example, Alice renames U to W. Bob relocates the parent of that node that was renamed to another place. This was the problem that we saw earlier where you would get that silent duplication. You don't get that here. The edit kind of moves with Bob's move because of the way the edges are set up. The edges are just changing the parent location, but everything downstream of that edge kind of gets moved along with it, and so everything commutes cleanly, and there's no conflict to resolve there. So now let's talk about conflicts. So conflicts are kind of inherent, right? You can't actually get rid of conflicts, but you minimize them and represent them explicitly. So here's a simple example. If Alice fills this hole here with x, and Bob fills it with y, well, there's no kind of obvious resolution to that, so you kind of punt it back to the two of them to resolve by representing it as a conflict, which is written like this. And in the graph, this is a multigraph, so you can actually have multiple edges labeled r coming out of plus, and that's fine. And it's just when we decompose this graph back to the term, it turns into a conflict because there's two things in this right position of the parent. Okay. Now you can also have relocation conflicts. This was what we talked about earlier. If Alice and Bob both decide to move the same thing to different locations. What's that? Okay. Okay, so similar idea. You kind of represent the conflict explicitly in the term because this is a node that has two incoming edges, which is not typically what you want in a syntax tree. So there's other things like this. Unicyclic relocations can happen if you do the right combination of moves, so we have a representation for that. Ultimately, what you get is a decomposition from graphs to groves, which is this idea of turning the graph into a collection of terms. I had suppressed all the unique IDs in the terms, but they're all kind of fundamentally there. And then we can decompose that set of terms into kind of like a classification, which we call a partition grove of like whether they have one parent, multiple parents, deleted, et cetera. So we have a little UI for exploring the calculus called the Grove Workbench that you can play with and instantiate with your own syntax tree representations. And then the kind of one last thing in the paper is so far we've just been talking at the syntactic level, but we also have a bidirectional type error localization system for groves based on our paper from last year. So I won't talk too much about that, but it's in the paper. Basically, we instantiate the system with a lambda calculus. We figure out all the ways it can go wrong, including merge conflicts of these various sorts. And then we assign a type system and a type inference system for that generates constraints between the conflicting things so that you can kind of like reason about programs with conflicts. So in the paper, full formalism, everything's mechanized in Agda. There's more details on the implementation there. I thought this was a nice quote. I'll just read the first bit of it. So this was from the developer of Darks in a paper called Theory of Patches. The fact that commutation can fail in Darks makes a huge difference in the whole patch formalism. It may be possible to create a formalism in which commutation always succeeds, ... This might require something like an anti-file, which would annihilate with the file when the file finally gets created. So that was like kind of the right track, this idea of a permanent deletion, but it wasn't the vertices that are permanently deleted. It's really, to solve this problem, you need to think about it in terms of edges being permanently deleted. So I'll just conclude with kind of the big vision that this project is a part of. So a quote from an interview by Alan Kay. Someone asked him about Wikipedia, and he said, it's a tremendous collaboration, but go to the article on logo. Can you write and execute logo programs there? No. So what if we had programs the size of Wikipedia being collaboratively edited live, type checked live? What if GitHub were truly a live commons instead of just a collection of siloed repositories? So this is exciting to you. Hopefully you can see how that connects to this paper. And there's a vision paper on some of these ideas from last year's POPL workshop at hazel.org. Happy to talk more about any of this. Thanks.
We have time for one quick question.
This is great. I take back what I said about I've been working with Hazel you've been talking about. It's pretty awesome, although I got it to hang several times when I did non-structured edit.
Production grade yet.
But it's super. This is so cool. What if I want to do this for TypeScript, like different languages? I mean, what do you need in terms of the language and the type system? Also the keywords to make this whole work.
Yeah, so I mentioned this Tyler system that another student in my group is working on, David Moon. So there you can kind of input the TypeScript grammar and get an editor like the Hazel editor. Hopefully a future project will be combining this paper and that paper, so you'll get a collaborative structure editor for free from the grammar. And then the type system, I think that's last year's paper, ... We could talk offline about it, yeah.
Thanks.
Thank you.
All right, so the next talk is biparsers exact printing for data synchronization. Rui Feng is presenting, and the stage is yours.
Okay, thank you. Okay. So hi, everyone. This is joint work with my supervisors, Tom Schreivers and Zhenjiang Hu. So as the title says, we are going to tackle the problem of data synchronization by using a technique called exact printing. And the final result of our system or theory or framework is called biparsers. So let's start with the problem itself, data synchronization. Here's a very simple example of the same data being stored in two different copies into different data storage formats. And as you can see, they are currently synchronized. So the synchronization between the two formats can be done by introducing a new shared data structure for both of the formats. And the transformation between the two can be think of as the composition of a parser and a printer. So we can see you can go from the left to the right by applying the parser of the right and applying the printer of the right. And the other way around is also works. So in the big picture, we have some textual representations, and we have a shared data structure. And we want a pair of parser and printers between each representation and the data structure. So this is what's expected from the whole synchronization scheme. If we start with a pair of synchronized data files, and we perform some edit on one of them, we expect to be able to synchronize the edit first back to the data structure, and then through the printer back to another data file. So as we can see here, we actually want to achieve some local edit, and we want the formatting of the original file to be preserved as much as possible. But this can actually go wrong and will go wrong if you are using some existing parser and printer frameworks to do this. So we summarize the problems as 2 challenges. The first challenge is the non-injectivity nature of the parser as a function. And this is in conflict with the requirement of exact printing. So we do the edit, and we try to print it back. And we see the edit is reflected back, but also the formatting is messed up. We see that the comments and the white spaces are lost. And the representation of the string data is in a different format. And also the written forms of the integers and the Boolean values are also in different format. So this is obviously not good. So the summary for this is that we need to remember the lost information of the parsing process somewhere. And we need to try hard to recover the formatting in the printing process. The second challenge is that there are some consistency issues between the parser and printers. So this time we apply a slightly different edits on the JSON file by introducing this suspicious colon space into the string. And if our printer tries very hard to preserve the original formatting, we get this file. And this is illegal. This is invalid syntax in YAML. And even if it is valid, this YAML file means something different because a string is turned into an object. So the summary for this is that we want to try very hard, but not to try too hard to recover the formatting. And we need to be careful when the text would change meaning. So our solution to this problem is our bypassers. Actually, if we put the parsing and printing aspects aside, we already know how to synchronize data. And the solution is called bidirectional transformation, or lenses. The idea is that we start with a pair of data, source and view, the 2 data to be synchronized. And we start with this original source. We perform a get operation to get the extracted view. And this get function is not injective. So that's where the non-injectivity problem happens. And we perform some edits on the view. We cannot directly put back the view alone because of non-injectivity. What we should do instead is that the get function should also extract something called a complement. And this complement saves the lost information in the get operation. Now we can combine the complement and the modified view so that we get back the updated source. This is very good, but pure lenses, they are pure, so that they cannot handle the parsing and printing effects. For composable parsing and printing, we already know that we need some P monad, the parser or printer monad, which is basically state monad plus error monad. So bypassers are essentially lenses, but generalized with monadic parsing and printing. So we combine the orange part and the green part into this definition. So we introduce the P monad into both directions of the lens and get the parse and print functions. And after this, existing definitions and properties for lenses also need to be generalized to take into account the new P monad. So the first thing to generalize is the basic correctness properties for lenses. which is called round-trip properties. It's a very happy thing to notice that generalizing the round-trip properties actually coincide with addressing the two challenges we have mentioned. So the first challenge was that the requirement of exact printing requires that every data that is parsed can also always be printed back to exactly the same form. So as an example, we have some different textual representations. They are parsed into the same thing. So apparently, if we directly print it back, then we get one of them, but not all of them. So this is not acceptable. Actually, we want them to be reflected back to the original formatting. This requires we save some complement, which is the lost information, to be able to recover the formatting. And the second challenge was consistency, so that every printed text can always be parsed back to the same data, so that the meaning is not actually changed. This is the example we see. So we have this colon space thing. If we print it with the unquoted format, then everything is messed up. But this means we have to print it in the quoted format, and it should parse into the same thing, and everything is good. The second thing to be generalized is the composition of lenses. So because we introduced the p-monad into biparsers, we changed from pure function composition into Kleisli composition of Kleisli arrows. So we see that the complement is accumulated. And the composition here actually combines two aspects. First is sequencing for the parser and printer effect, which is the P then Q structure. And it also has the piping structure for transformation. So the first transformation is from X to Y, and the second is Y to Z. So the combined thing is from X to Z. And our main result here is that this composition operation, this generalized composition, preserves the round-trip properties, which enables compositional programming so that we can actually combine small biparsers into larger biparsers. And during this process, all the round-trip properties are automatically derived. So we automatically get the correctness guarantees for them. And based on this definition, we provide a rich combinator language to write biparsers, which we call biparser combinators, which is based on the classical parser combinator frameworks, like Parsec in Haskell. So usually, these frameworks consist of 4 different parts: token consumption, sequencing, and alternation or choice, and filtering, which is validation and transformation. So by analogy, we define biparser combinators. The main challenges here are that, first, to take the complements into consideration, and second, to make sure that all these combinators preserve the round-trip properties. As I have already mentioned, that composition is sequencing and transform combined, so we have already 2 of them addressed. And actually, the hard part is for the choices. I will not go into all the technical details. I'll just show you an example. This is a grammar for JSON strings. It's simplified one. So as you can see, we have all these EBNF generation production rules. And we can just directly follow the structure of this grammar to define the parsers using parser combinators. And the parser resembles the grammar structure. So we have the combinators for sequencing, combinators for alternation, and combinators for transformation. So the same thing would happen for biparsers. As you can see, this page is very similar to the previous one. So that means the biparsers also resembles grammar, but it also resembles the parsers, which means if we want to develop the biparsers from scratch, we can do it easily by following the grammar structure. But if we already have some parsers, we can also migrate it fairly easily. So here are some highlights of our solution. First is that we made it compatible between lenses and effects. So as some of you might know, in previous works, there are some serious restrictions on how effects can be used in bidirectional programs. We solved the problem for parser and printer effects specifically in 2 key points. So first is we use complement-based lenses instead of the SV to V-based lenses. This avoids getting into lens compositions, which makes the composition preserve the round trip properties. And it also has some other benefits, which you can check the paper to see. And the other thing is that we require effect cancellation instead of effect preservation, as in previous works. So this means print would rewind the effects performed by pars and vice versa. And this fits our purpose perfectly and simplifies the theory. The second thing is what I mentioned just now, the choices. So for a parser framework, we need backtracking choices. But in a bidirectional parsing context, there are some consistency hazard happening in the choice combinators. Because parser combinators rely on shallow backtracking for choices, which means if you have a P or Q structure, first P is attempted, but only if P fails, we fall back on Q. This means if we have this situation, we start from some X, we parse and we parse with P and fails. Then we fall back to Q, which succeeds. And then we attempt to print it back. But since P is still attempted first, and it might succeed in this case, in which case the Q branch is never attempted. So this results in some inconsistencies between which branch is actually chosen in the execution. But parse Q and print P are completely unrelated, so they have no guarantees whatsoever, which means this round trip, we have no guarantee for it. The solution here is that we have some different choice combinators for different preconditions, which would ensure that no such branch mismatch would happen. And there are some more features, you can check them out in our paper, and I will not get into the details. Finally, we have a complete proof and a runnable example. So we implemented the whole framework in Agda and Haskell. We have mechanics proof in Agda, all the combinators with the round trip properties verified. And we also have a runnable example for subsets of JSON and YAML. And both of them are available as reusable packages, so you can check them out. Finally, to conclude, we present bypassers with exact printing and for data synchronization. This is lens generalized with monadic parsing and printing. We have formalized consistency for it, which is the round trip properties. And we also support compositional programming with this main result. And we provide a rich collection of combinators to construct practical bypasser examples. And yeah, thank you. And more details in the paper.
Any question for the speaker?
Just a small one. I think I saw it flash by on one of your slides, but you can use this as just a pretty printer, right? For like, if you have a data structure, you could throw it through the pretty printer, and you don't need to have some weird special context in terms of an original parse in order to use this.
Right, you can. The problem is, as you see here, the formatting is lost. So I think in a lot of actual situations, for example, you have two people collaborating on the same data source and they have different preferred data formats, then it wouldn't be very polite to see that your formatting is lost after my change. So I think that's one of the fundamental flaws of existing pretty printers.
Thank you.
Hi, I'm Paponia from Minnesota. And I have a question about the preserving the format. For example, if I change the word status to some word that is very long, will the properties and the YAML file still be aligned?
Right, right. That's something you need to take care of when you write the bypassers. So there are actually something we sorry. No, sorry. Anyway, we have this view complement alignment operator, which allows you to adjust the internal structure of the complement. So as I said, all the white spaces and comments, they are saved in the complement to be recovered. And you get an opportunity before printing to actually manipulate the complement to fit your purpose. And yeah, so that is possible, but you need to do it manually.
Hello. Nice work. I have a question of when you apply a choice combinator and the first phase fails or success. I mean, the second case success, and you print it back. You said it might be that the first branch succeed. Why would that would happen? Like right here.
Yeah. So this is only one of the example. You can also have print first, and the second branch of print succeeds, and the first branch of parse succeed.
Yeah.
So you also have a mismatch there. To prevent both of them from happening, we have some special preconditions for applying the choice combinator.
Yeah, the question I'm asking is what would make those like, what kind of inconsistency is there?
Okay. So because if you have the parser from P and printer from Q, you essentially have no guarantee about their relationships, right? So if they are from the same bypasser, then you have the round trip properties. You are guaranteed that they are consistent and you get the exact printing behavior. But if they are from different bypassers, then you know nothing about them, which means anything can happen.
So it means in general choice, the alternate combinator is just not round trip, so correct or something like that?
Yeah, so if you do not pose any requirements on the two branches, then anything can happen. You have no guarantee.
Thanks.
All right, then this concludes the session, and let's thank the speaker again.
Are you turning them on? Okay. If everyone could have a seat. We're about to start the afternoon session on program logics. Okay. So, there you are. All right, so the first talk in the session will be given by Max, talking about program logics a la carte.
Thanks for the introduction. My name is Max Wistrup, and this is joint work with Michael Samler and Ralph Young. So here's a story, and perhaps it's a familiar one. We have a young researcher who sets out to define a programming language, language 1. Perhaps this programming language supports certain effects. Perhaps there is an output effect, programs can write to the console. Perhaps there's also a crash effect. Certain programs are malformed, and therefore they crash. And perhaps there's also a heap effect, which is to say that certain programs may want to read or write memory. Now, the researcher is interested in proving certain programs to be correct. That is to say, proving the absence of bugs. There is one good way of doing so, which is to devise a program logic. So that's what the researcher does. They devise a program logic, logic 1, that is tailored for this programming language, language 1. So a program logic typically consists of two things. So for one, it consists of a number of proof rules that you can make use of in order to build up proofs for correctness of programs. Furthermore, it also has a soundness proof, which guarantees that these proof rules are indeed correct. Now, sometime later, this programmer or this researcher might be interested in a new programming language. Perhaps they devise a new programming language called language 2. This programming language might have another set of effects. Maybe it has crash effect, maybe it has heap effect again, but maybe it also has concurrency. Again, the researcher is interested in proving the correctness of certain programs. So they, again, do the same rigmarole of defining and establishing a program logic now tailored for this new language, language 2. Notice here that the two languages, language 1 and language 2, share a significant overlap. We can quantify this overlap by looking at what are the effects that are shared. So in this case here, we have that the crash effect and the heap effect appears in both languages. So one concrete consequence of this significant overlap is that there are certain proof rules that appear in both of the program logics. So for instance, you might have a load rule, which looks something like this, that appears in essentially the same form, whether in logic 1 or logic 2. There is one unfortunate fact or consequence of this, which is that when you come down to logic 2 and you want to establish its soundness, you are incurring duplicated proof effort, right? You've already proven this proof rule to be sound when you established logic 1, and now you're establishing logic 2 and you're doing the same thing again. So this is a frustrating situation because it means that researchers are again and again defining new program logics, proving them sound, and is doing much of the same work over and over again. So this seems to evince the need for some kind of lacking abstraction that can streamline the process of defining new program logics. And it is the purpose of this work to establish that abstraction. So let me just sort of adumbrate like a very high-level overview of our solution. So in our view, we take a language like language 1, and we view it as composed of certain effects. In this case, there are 3 effects that we've identified. For each of those effects, we take a corresponding program logic fragment. So you can think of a program logic fragment as kind of a program logic that pertains to a particular effect. These are defined in our theory or in our library. Then we put together these program logic fragments in order to obtain a program logic tailored for our particular language. So essentially, we obtain these program logics by composition. Now, to be slightly more concrete, what we are doing in order to implement this solution is the following. So we are interested in defining a language-specific program logic. Now, this language-specific program logic comes in the form of a Hort triple, like this. So the first thing we do is we take this expression in our programming language, and we denote it into some kind of language-agnostic domain that captures the semantics of this expression. Once we have done so, we take the Hort triple of that denotation with respect to a language-agnostic program logic. To distinguish between the language-specific program logic and a language-agnostic program logic, what we do is we use these double curly braces. So that is the idea. We define a language-specific program logic as a thin wrapper around a language-agnostic program logic. Now, let's take a look at this language-agnostic domain. So we are in search of a denotational domain that can capture the semantics of expressions, whether they're in language 1 or language 2 or any number of other languages. So for this purpose, we choose I-trees, which is a denotational domain that is established in prior research, and they've proven to be very convenient and successful at modeling the behavior of programs. Now, you don't need to know much about I-trees in order to follow this presentation, but there is one thing you do need to know, which is that it's a data type like this, I-tree ER. And there are two parameters. So first, there's the E, which is the set of effects that the program can exhibit. Secondly, there's the R, which is the return type. That is to say that I-trees have the capacity to return a value, and this value will be of type R. So let me just give a brief overview of the structure of the rest of the talk. So the first thing I want to discuss is this language-agnostic program logic. And this comes in the form of a program logic for arbitrary I-trees. With that, we are going to give an easy and compositional recipe for defining your own custom program logics for your own custom programming languages, or existing programming languages for that matter. Then, to exemplify how this would look in practice, we are going to give a small demo example and see how this recipe is implemented. So let's take a look at this whole logic for general I-trees. So this comes in the form of a whole triple, where the T here is an arbitrary I-tree. So that is to say that this E is an arbitrary effect set. We are not tied to a particular choice of effects. It's arbitrary. What this whole triple is supposed to codify is something like what appears on the right-hand side, namely that if the precondition is satisfied, every execution of the I-tree goes well, and the output will satisfy the postcondition. Now, there's one caveat here, which is that the effects in E do not carry any logical meaning just yet. So it's necessary to endow them with a logical meaning. And this is where this subscript H comes into the picture. So H is what we call a logical effect handler, and it specifies an axiomatic semantics to the effects in this effect set E. That is kind of the datum that is the input to our definition. Once you have that, you get, from our theory, this definition of a Hoare triple for I-trees with effect set E. Furthermore, there's a theorem in our paper that I will not discuss so much today, but that ensures that this Hoare logic for I-trees is in fact sound. Now, there are certain rules that come for free with this definition. And I emphasize for free, right? You don't need to reproof these rules for every effect set E. So the first one is a familiar rule. It's a consequence rule, right? It's well known from Hoare logic. Furthermore, we're actually working in a separation logic, and we get a frame rule for free. Then there are certain rules that pertain to the monadic structure of I-trees. So I-trees are a monad. What that means sort of concretely is that you can sequence computations. So if you sequence two computations together in the I-trees, then you, in order to prove the Hoare triple for such a sequence computation, all you have to do is to prove the Hoare triple for the first computation and then the second computation. And this idea is exactly captured by the spine rule. Furthermore, there's a rule that says exactly what you have to do in order to prove the Hoare triple for an I-tree that just immediately returns a value. Now we have all the ingredients to set out a recipe for how to easily define a program logic. The very first step of this recipe is that you have your language, and you want to identify what are the effects that programs in this language can exhibit. So you build up an effect set. The way you do this concretely is by pulling common effects from our library, from our theory, putting them together. Now, it might also be that your language has some more esoteric features which necessitate custom effects. And in that case, you'll have to define your own custom effects, but you can put them together with these common effects. Once you've done so, you need to specify the semantics of the language. And the way we do that is by means of denotation. So you define a denotation that for each expression in the language associates an I-tree that captures the behavior or the semantics of that expression. Then you need to choose a handler. And the way this might seem like a complicated thing to do, but it's actually fairly simple. For each of those effects, E1, E2, and so on, that you pulled from the library also provides corresponding logical effect handlers that deal with those effects. And so you just put those handlers together, and in this way, you obtain a handler H. Now, this is exactly what I mean when I say combining program logic fragments. Each handler, say H1, H2, engenders a program logic, and we're putting those together in this step. Namely, to define the Hoare triple, we use the denotation, and we use the I-tree Hoare logic according to this formula I already showed. Then, finally, you have your proof rules that you're interested in proving sound. And to do so, what you do is you use the Hoare logic for I-trees in order to do these soundness proofs. That is to say, we have these rules that I already wrote up before, and you can use those in addition to other rules that I've not displayed yet. So in order to illustrate how this would work in action, I'm going to show it by means of an example. So this example is, I call this lambda h. It's a small language. It's a lambda calculus that supports heap manipulation. So I have excised most of the definition that has to do with sort of the lambda calculus aspect of this language, just to focus on the memory aspects of this language. So for the value case, there is one new kind of value, which is values that are denoted by L. These are the locations of the language. These are locations of the heap. Then there are three new kinds of expression. One is the allocation expression, which allocates a new heap cell. Then there's a load expression, which loads from a location. And then there is a store expression, which stores at a location. So in order to implement the recipe, what we have to do is we have to give a denotation. So that is to say, for each expression in this language, we're going to associate an I tree. In this case here, the effect set is going to be composed of the crash effect and of the heap effect. We'll see in a moment why these are the two relevant effects. Now let's focus on just the denotation for the load expression. So the denotation will look something like this. First, we take the argument of the load, and we evaluate that down to a value. Once we have done so, we assert that that value is in fact a location. If it is not a location, we do a crash. So this here is marked in, the crash is marked in red, which is to say that it is what exhibits the crash effect. Once we have done so, we exhibit a load event to load from the memory. This is marked in blue because it marks the heap effect. And finally, we return the value that we loaded from memory. That is the denotation of load. With this at our disposal, we can define the Hoare triple for our particular language, lambda h, according to this formula. To do so, we need to choose a handler h. Now, we know the effect set E was composed of the crash effect and the heap effect, so we simply compose the corresponding handlers to build up the handler h. Then we need to derive our proof rules for this program logic lambda h. And let's just focus on one proof rule. So I want to focus on the load rule. Maybe this is a familiar load rule if you know about separation logic. It says that in order to do a load, you need permission to do so, and the permission comes in form of this points to resource. Now, remember that we defined our Hoare triples as just a thin wrapper around a I-tree Hoare triple or a language-agnostic Hoare triple, and therefore, it actually turns out that this load rule is an easy consequence of a more general load rule. I call this the load rule to rule them all. This rule is a part of the program logic fragment for the heap effect. Now, what is the significance of this? Well, it means specifically that if you have any number of program logics in which this load rule appears, in order to prove the load rule sound in any of those program logics, all you have to do is to leverage this general load rule. That is to say that we do not incur this duplicated proof effort when we define new program logics like this. And I think this is the key point. If you want to take anything away from this presentation, it's this. The theory here allows us to make use of language-agnostic program logic in order to build language-specific program logic. Basically, it adds this layer of abstraction, which comes in the form of the I-tree Hoare logic, that you can use when you're building up these complicated soundness proofs or your complicated custom program logics. So that in particular means that you get to leverage all the good qualities that you know and love from program logics, like reuse and separation and compositionality and local reasoning. You get to leverage those when you build your program logics. And I think that is quite neat. So as a kind of conclusion here, I want to summarize some aspects of program logic fragments. So we had this example language, lambda h. We viewed that as built up of these two effects, a crash effect and a heap effect. Then we took the corresponding program logic fragments, we put them together in order to form a program logic that is tailored for lambda h. A program logic fragment consists of the following pieces. So for one, it consists of a logical effect handler. That is what defines the program logic fragment. Furthermore, it comes with certain proof rules. So for instance, in the case of the heap program logic fragment, it comes with a load rule. And furthermore, it also comes with a soundness proof that it guarantees that those proof rules are indeed correct. So here's some things that are not covered in this talk, but are covered in the paper. So if any of these things pique your interest, you can check out the paper. For one, we have a formalization of the entire theory in ROC using iris, the iris separation logic. Furthermore, we have a very nice logical treatment of cooperative concurrency, which we use to model preemptive concurrency. Then we have a good account of compositional soundness proofs. So we have soundness results for each of these program logic fragments, and we demonstrate how you can put those soundness results together in order to obtain soundness for the entire I-tree Hall logic. Then we have support for angelic choice, and moreover, we have support for mixed angelic and demonic choice. This is something I'm quite proud of because this often presents a difficulty when you're working with program logics. And we have a unified account of termination-sensitive and termination-insensitive reasoning within one framework. And then finally, we have some case studies. So we have an ML-like language known as heaplang. This was established in the IRIS line of research. And we also have a realistic model for assembly known as ILARIS, which is established in the Samla et al. Work. And in each of those cases, we demonstrate that there is, in fact, less proof effort needed. So I hope some of these points can convince you that this theory is not just meant for toy examples. It is actually possible to invoke this theory at scale for realistic programming languages. And that is all I got. Thank you for your attention. I'm happy to attempt to answer any questions.
Microphone.
Thank you. First of all, here. That was a great talk.
Thanks.
I have like 3 questions I need to select. First of all, in realistic languages, the load rule would be very different for each language. Like loading a value in C is very, very different from loading a value in JavaScript or in Java. So how much for real languages do you think you can reuse stuff?
I would say so. You have your denotation for load, whether it's in C or JavaScript, and that might do all sorts of complicated things, right? It might say, oh, if you do this, this would be UB, and we exhibit a crash. But when you're approving the load rule, you're making use of, in particular, this bind rule that I showed to kind of step over the individual components of your denotation for load. And then at some point in that denotation, there will probably be exhibited a load effect that interacts directly with memory. That is where we invoke the load rule. But that doesn't mean that there isn't all this like complicated reasoning on the I-tree Hall logic level of abstraction that describes what happens in these cases where there's UB or something. So it's just that the load event maybe appears inside somewhere in this denotation.
Okay.
Yeah.
I will go offline for the next one.
Right.
Oh, we'll get to you.
We'll get to you, don't worry.
We'll get to you, don't worry. There's time.
Over here now.
Yes.
Yeah.
I wanted to ask how you handle higher order programs, given that with I-trees you have predicativity restrictions of inductive definitions, so it's hard to have intermediate computation results using the same type.
This is a very good question. And in fact, one of the case studies, heaplang specifically, has higher order. You can store lambda terms on the heap, and we support that. There's no issue. So the trick is a bit like we have 1 foot in the semantic world and 1 foot in the syntactic world. So specifically, when we store stuff on the heap, we store the syntactic representation of the lambda term. Then when we pull it from the heap, because there's a fixed point combinator for I-trees, there's no issue. We can actually evaluate that. However, this is maybe not an entirely satisfactory account if you're interested in equational reasoning, because the bisimulations on I-trees are too strong when you have like syntactic representation. And this is what gives rise to maybe the interest in something like guarded interaction trees, which are entirely denotational, right? You can do equational reasoning, but also limited in some ways, at least at the present moment, to my knowledge. Like there's lack of support for non-determinism and for concurrency. But nonetheless, we sort of use the syntactic representation in order to deal with this issue. Yeah.
Yeah.
Your approach is based on the fact that if you extend the language, you just add more effect, but you don't change the previous one.
Yes.
And this is not general, because, for example, take our logic for sequential program. Suddenly you go to concurrency, but with weak memory model. And then the evaluation of an expression becomes completely different.
Right.
The previous logic is no longer valid.
So I don't know much about weak memory, but I can tell you what happens in the...
It's very difficult.
Yeah, that I believe. I've heard rumors, right? But I can tell you what happens when you go from sequential to concurrent. In fact, you do just add another effect. It doesn't break the previous effects. However, the way we treat concurrency, we model is using what is called using cooperative concurrency. So that is to say that if you just add the concurrency effect, and then the same programs will still verify because you don't have these yield expressions anywhere in the program. So the difference, the breakage really comes in when you're inserting the yield expressions.
Does not answer my question.
No, maybe it doesn't. No. Yeah.
You can apply the previous thing.
Yeah, I mean, there's also an entire line of research that sort of does this weak memory modeling in Iris, but I'm not so familiar with it.
I think it's a good discussion to take offline.
Yes.
Let's thank Max again for a great talk. You may need to. You want to mirror?
Sorry,
you may need to mirror the thing.
Oh yeah, please.
So our next talk will be given by Freek, who will tell us about extending incorrectness logic with backwards reasoning.
Yeah, thank you. Yeah, everybody can hear me? No? Sorry about that. So not. Now it works. Yeah. So like here. Sorry about that. Yeah, okay, now I'm, yeah. Okay, sorry about that. So this talk is about extending incorrectness logic with backwards reasoning. So let's say that you have a program that takes as input a list of elements, and it shuffles these elements into a new list. Let's then say that you want to prove, using a program logic, that indeed this program can produce at least all possible permutations of the input list. Or let's say that you have a program that computes a certain variable y with some convoluted expression or with some convoluted program, and you want to prove that at least the result y is 0 is possible. So this program may produce a lot of results, but at least you want to show that the value y is 0 can be reached after execution of this program. With standard Hoare logic, this is not possible, because Hoare logic expresses basically what can happen at most. If you have a triple P, C, Q, then Q states what can happen, gives an upper bound to the things that can happen from states that satisfy P. Instead, incorrectness logic reasons over what can happen at least. And you can see this from the definitions. So Hoare logic is defined as the post set of P is a subset of Q, meaning that if you start in states that satisfy P, you run your program, then you will always end up in a Q state. But incorrectness logic talks about what can at least happen, and it's formulated as Q being a subset of the post of P, meaning that for all the states in Q, you know that they are reachable by executing program C from a state that satisfies P. In other words, it shows a certain type of liveness, whereas Hoare logic shows a certain type of safety. And you can see this also from things like postcondition weakening versus postcondition strengthening. In Hoare logic, you can do postcondition weakening. You can weaken it all the way up to true. And that basically means then what you then say is, well, what can happen at most? Anything. And that becomes a trivially true statement. Whereas for incorrectness logic, you can do postcondition strengthening. And you can strengthen it all the way to false, basically saying that for 0 states, I prove that these are actually reachable. Now, with this question in mind of what can at least happen, how can we use this incorrectness logic? Well, the way that Peter O'Hearn uses it is that Q characterizes a bug, and we aim to prove existence of this bug. And that's why it's called incorrectness reasoning. So we want to prove that the program can at least exhibit the bug, and that means that we have no false positives. But in the reverse Hoare logic paper, it's also used as a correctness type of reasoning, where Q characterizes some form of specification, like with the shuffle function, and we aim to prove correctness with regards to that specification. And finally, we can also, the way we also want to use it is where we have some assertion in the program, and we just want to show, can we at least trigger this assertion? So with these use cases in mind, it makes sense to think of the following question. Can we now do backwards reasoning over incorrectness logic? In other words, if I give you a Q, this assertion or this specification or a characterization of a bug, and if I give you the program, of course, can we now define a function tau that takes these two as input and produces a precondition or presumption, such that an incorrectness triple holds? In other words, can we go from an assertion back to the entry point of a function or of a program? And the answer basically is, well, no. And to see why, let me use an example. So here we have a very simple program. Y gets assigned x plus 1. And we want to see whether states where y is equal to 10 are reachable after execution of this program. And I think everybody here would say, well, sure, this is reachable. Just start from a state where x is equal to 9. But that is not a valid incorrectness triple. As a matter of fact, for this result, there is no correct incorrectness triple. And the reason is that incorrectness reasoning treats the result as by saying that all result states should be reachable. And y is 10 formulates a large set of states, because it also formulates states where y is equal to 10, and for example, x is equal to 0. And that state is not reachable. If I would want to prove that states where y is 10 are reachable using incorrectness logic, then I would have to have started with a result y is 10 and x is equal to 9. And then I could show that these are reachable from a state where x is equal to 9. But this is, of course, very unsatisfactory, because if I want to characterize some bug, what this basically means that I would have to start from a result or a post condition that precisely defines constraints over all variables in the state. And that's just infeasible and impractical. So I don't want to need to define anything over x if I just want to know whether states where y is 10 are reachable. So what we added to incorrectness logic is a notion of underspecification. And it allows you to say, I want to look at states where y is 10, and I want to see if those states are reachable. And I treat x, I underspecify variable x, meaning that x is irrelevant. So this triple holds. States where y is 10, where I don't care about x, are reachable from some state where x is equal to 9. As a matter of fact, I can make it stronger and say states where y is 10, where I don't care about x, are reachable from some state where x is equal to 9, where I don't care about y. The value of y is irrelevant because no matter what value it has, the result will be reached, since y is going to be overwritten anyway. So this enables backwards reasoning. So what we have actually contributed is that we have extended incorrectness logic with this notion of underspecification. We have then built this proof system that you see here on the right-hand side of the slide. And this proof system is constructed in such a way that in the conclusions of all these rules, the result or the post condition is just some Q. And it shows how you can go from this Q to a presumption or precondition. In other words, it can be used to do backwards transformation. Of course, we have proven soundness of this proof system, which in this context means that triples hold, or in other words, that there are no false positives. We have also proven completeness for a subset of programs and predicates, and the exact definition of that is, of course, in the paper. Finally, in order to put this in practice, we have defined some proof tactics. One of them has to do with finding the right values to instantiate these rules, and we show how SMT solvers can be used for that. And the other one is how to treat with loops, and I'll talk about that a bit more. Finally, we have an implementation of a prototype and applied it to get some experimental results. So let's take a look at one of these rules. I think actually for this proof system, the assign rule is the most interesting one. So here you see it on the top of the slide. And the first thing that you see is that there is a bit of, let's say, management of which variables are relevant and irrelevant. So let's say that I have a variable x that is considered to be irrelevant, and it's used as an input for computing a value for y. So the y is going to be assigned f of x. If the value of x is irrelevant in the conclusion, then it's going to be relevant in the presumption, because its value is I need to define constraints over this variable in order to make the result reachable. But y itself is, so x is removed from the set of irrelevant variables, which happens here, but y is added to the set of irrelevant variables, since it's going to be overwritten anyway. Then, how to now actually compute a presumption from a result? Well, at the heart, it's just standard substitution, as the way it is with standard OR logic. So in Q, you do substitution, where you replace occurrences of y with what it gets assigned to. But there's more to it. First of all, there is a side condition. So the side condition states that the result Q should be sufficiently strong to prove that y is in the image of f. So why is this? Well, if this is not the case, that means that Q models some state where y is not in the image of f. In other words, y cannot be computed using this function f. It cannot possibly be an output of function f. And that would mean that Q models at least one state which is unreachable. And since incorrectness logic reasons over triples where all result states must be reachable, this side condition is necessary. Now you can see that there's still more to this one rule. And to explain the rest of this rule, I need another example. So here we have an example where y gets assigned to x plus 4 modulo 7. And now I want to see whether states where y is equal to 4, whether those are actually reachable. So they are reachable. So for example, from a state where x is 0, if I then do x plus 4 modulo 7, I get into a state where y is equal to 4. Now, if I would do standard substitution, then what I would get as a presumption is the set of states where x is either 0 or 7 or 14, etc. X is 0 modulo 7. That's what I would get if I would just do standard substitution. But that is a large set of states. X can be either 0, 7, and so on. And since we are talking about reachability, it suffices to find only a subset of that states, because I only need to find basically one path that that triggers the result. So here I want, instead of formulating that x is 0, 7, 14, etc., I want to be able to prove that just the state x is 0 can trigger this result. So that's called zooming in on a specific value. And this is more than just for sake of, let's say, completeness of the logic. It's even more than for sake of precision. It's actually crucial that we can do this for the sake of composition. Because if you want to use this established triple compositionally, then it may be hard to, or impossible to show that states where x is 0, 7, where all those states are reachable. It may be the case that they are not all reachable, whereas if I zoom in on this specific state, that state may be reachable. So the rule supplies you can instantiate this rule in such a way that it allows you to zoom in on specific values of variables. So then the while rule. Now I won't explain it in all detail, but what's most important here is that similar to the zooming in that I just explained, since we are talking about reachability, we don't necessarily have to have loop invariance. If the result is reachable after 0 executions of the loop, then you can just treat the loop as a no-op and just see if, well, then approve reachability in that way. In other words, the while rule requires you to find an iteration count of how many iterations the loop is the loop body is being executed. And in order to find these iteration counts, we found that the concept of loop summaries is very useful. So these loop summaries, they basically summarize the values of certain variables in the nth iteration with a closed form expression. Now we have done an evaluation. We have used the svcomp benchmark suite. And this was very useful for us because this actually comes with a ground truth. So it contains a lot of programs. These are categories of programs. And for all these programs, they contain assertions with annotations whether these assertions are reachable or not. And in that way, we could first evaluate soundness. So if the assertion is known to be unreachable, do we actually generate an unsatisfiable set of side conditions and a presumption? Now, of course, since we have proven soundness in the Isabelle theorem prover, the percentage of functions for which this holds should just be 100%. We are sound, so it should simply be 100%. But you can see in the highlighted column that this is not the case. Actually, it's very often below 100%. And the reason is that these programs contain certain constructs that we do not support yet, such as floating point computations or variables in loops that we could not summarize. And what we have done is that we have treated those constructs over approximatively, saying that basically those variables, anything can happen to them. And that causes, then we proceeded with the presumption generation over the parts of the state that we could deal with. Then what we also want to evaluate is a certain type of preciseness. So if you think about it, we are trying to do reachability, and we could have just done sort of fuzzing, right? Where you start basically from any state, take true as a presumption, and compute the post set from there. Instead, we do this backwards reasoning that gives us a presumption, and we want to show that this presumption is actually significantly smaller than just the entire set of states, the entire set of initial states. And this, so we have measured this reduction factor and found that this actually, that the generated presumption very often is significantly smaller than just doing fuzzing. Now, as next steps, one of the things that the table that I've just showed shows is that we need better loop summarizations. So we have implemented sort of a naive technique that only deals with linear variables. And with stronger loop summaries, we would be able to capture more variables, and that would lead to better results. I want to be able to apply this kind of reasoning actually to more lower level code, for example, LLVM. And then we get into challenges that in lower level code, point arithmetic often becomes very complicated, and that there's just an absence of actual syntactic control flow structures. Instead of while loops and if statements, you have a control flow graph, and it's not always possible to just transform a control flow graph back into syntactic control flow structures. And the final thing is that in order to make this scale, I want to do have a compositional approach with respect to function calls. And of course, this sort of shouts that we should do separation logic. And I'm really interested in seeing how the notion of under-specification of variables combines with separation logic and incorrectness reasoning. So with that, I conclude and want to thank you for listening.
All right, we have time for 1 or 2 quick questions. What?
If I'm wrong, is it fundamentally boiled down to the invertibility of the functions? So if you have in your example, you have function f, if it's non-invertible, how does it work?
So let me show the rule here. So if I heard you correctly, the question is like, well, if f is not invertible, how does it work, right? So indeed, the rule requires you to find an inversion of f. Exactly. If you cannot invert f, then you cannot apply this particular rule. So then it would not work. Yeah.
So your theory is sound on the assumption that the function is only invertible.
Yeah, exactly. Yeah.
Last, yeah, question back there. Quick one.
Thanks for the talk. So when you had the example, the motivating example as the start, I just thought you could use Lisbon logic, or also called sufficient incorrectness logic. So what would you say are the advantages of your approach?
Yeah, so Lisbon logic formulates another type of sort of reachability, right? Where you say that all states that satisfy the precondition will lead to the postcondition, whereas incorrectness logic says that all states that are modeled by the postcondition are actually reachable. I'm not here to argue which one is better, or, both have their use cases, obviously. I actually think that this is a particular example which actually highlights specifically incorrectness logic, where you would want to say, well, I want to prove that all possible permutations are really reachable. And I think this is something, if I'm correct, that you cannot do with Lisbon logic.
All right, let's thank Freek again. All right. Our last talk of the session will be given by Noam, who will tell us about the latest advances in outcome logic.
Quite the latest.
What? Not quite the latest. Not the latest.
Okay, thank you, Derek, for the introduction. So this is joint work with my collaborators Dexter Kozin, Alexandra Silva, and Joe Tasserati. Okay, so this logic is about randomized nondeterminism. When we say randomized nondeterminism, what we mean is we have a language that has 2 different choice operators. One is for nondeterministic choice, so this is the ampersand symbol that you see. And we can think about this kind of as like an adversarial choice or demonic choice, where we have no control over how the choice is going to be made, so we have to assume it's going to be made in the worst way possible. The second type of choice is probabilistic choice, which we denote with the O+. And this is a quantitative choice, so we know precisely that the first choice, C1, will be made with probability P, and the second will be made with probability 1 minus P. Okay, so in order to make the semantics of this language compositional, we use the convex power set. I'm not going to talk too much about what this is, but basically the takeaway is that when we talk about these non-deterministic or adversarial choices, it's not just that the adversary can choose between the 2 options, but rather the adversary can choose a distribution over the 2 options. So even the non-deterministic choices are somewhat probabilistic. Okay, so let's look at some programs that we can express in this language and how to interpret them. So here we have 2 variants of a coin flip game. The idea is that you have a fair coin flip shown in blue, and you have an adversarial choice shown in red. And depending on how we compose these 2 programs, we can get scenarios where the adversary can guess the coin flip or the adversary cannot guess the coin flip. So if the coin flip again. Try it now. This one? This one? Does this work? Okay. Okay, great. If the coin flip happens first, then the adversary can guess the result. If the adversary guesses first, then of course it can't guess what the coin flip is going to happen. Another way we can understand the difference between non-deterministic and probabilistic choice is through equations. So here we have 3 equations to describe non-determinism. The first one is an idempotence property, so it states that if you make a choice between some element and itself, it's the same as not making a choice at all. And then the second 2 properties are about reordering choices. So if you reorder choices, you get the same semantics. For randomization, we have very similar equations, but now they're quantitative, so that when you rearrange choices, you need to also adjust the probabilities. And then we can also reason about the combination between these effects, the interaction between these effects using equations. So for that, we have a distributive law, where probabilistic choices distribute over non-deterministic ones in a very similar way to how multiplication distributes over addition in standard arithmetic. And so this kind of confirms our demonic interpretation, where we want to be able to know for every choice that the adversary makes, what is the distribution of results that we get. Okay, so this paper isn't really about equational reasoning. These equational properties are pretty well known at this point. But part of what we wanted to do in developing a logic was to take these intuitive equational properties and reinterpret them as propositions. So instead of equality, we now have if and only if, and we can think about the P's and Q's as being assertions about the program state. And so what these assertions roughly mean is that when we have the O plus, we have 2 assertions, and we say that the assertion P occurs with probability P, little p, and the assertion Q occurs with probability 1 minus P. Then when we have an adversarial choice, what this is basically saying is that the adversary is picking the probability that each one holds. Okay, so now using this assertion language, we can start to develop logic where we can express properties about programs. Here we have a post condition for this coin flip game program, where we exactly specify the values of all the program variables. Now this clearly does specify what the program does, but it's kind of obfuscates the meaning because there's so much detail here. And this is where the benefits of propositional reasoning come in, because we can actually weaken this assertion to not specify the exact values of all the variables, but rather just specify whether x is equal to y or not. And then we can continue to use the propositional laws, so we can use the commutative law on the second sub-expression to flip around the order. And now we have the same assertion on each side of the ampersand, so we can collapse it with the idempotence rule. And now we have a very concise assertion about the program, which just says that x equals y with probability 1/2. And x equals y, I mean, if you remember from the program, x was the result of the coin flip, y is the adversary's choice. So this essentially says that the adversary can't guess x with probability better than just flipping a coin. And so we can put this into a triple to create a program logic. And we call this logic demonic outcome logic because we have outcome reasoning, sort of about probabilities, and we also take a demonic view of non-determinism. So the post-condition applies to every possible choice that the adversary may make. And this logic has pretty nice reasoning principles. So we have nice compositional rules like you would find in Hoare logic. We also have nice probabilistic reasoning rules like you would find in outcome logic. So what this rule says is that if you have a probabilistic choice between 2 commands, and you know what happens when you execute each of those commands on their own, then you know that the outcome of the first program occurs with probability p, and the outcome of the second program occurs with probability 1 minus p. So this is pretty nice. But somewhat interestingly, the analogous rule for non-deterministic choice is not sound. And just to give a little bit of intuition why it's not sound is because this rule doesn't respect the distributive law that we saw earlier on. So to see this a little bit more concretely, we can look at an unsound derivation using that invalid rule. So here we have a scenario where the precondition already has some information about a distribution of outcomes. And we can kind of think of this as being like the adversary already knows the distribution over x before it makes its choice. And so using the invalid rules, we derive a specification for this program where it basically says that the adversary cannot guess x, but that's not true. And we can start to see what goes wrong by looking at the initial post condition, where we have, I mean, we can look at this post condition and think about it kind of like a tree. So you have the ampersand at the root, and then you have two subtrees with these O+. And so what this tree is essentially saying is that the non-deterministic choice happened first, and then the probabilistic choices happened afterwards. And that's clearly not true, according to what's really going on here. So using this rule is unsound. So what do you have to do instead? Instead, we can only use the rule in a restricted way. So if you want to analyze this program, you first have to break up the two probabilistic outcomes. We can then reason about the program and each of the probabilistic outcomes, and then stitch them back together. So here we see we have the blue derivation and the red derivation for each of the probabilistic outcomes. They come together, and then we can apply more propositional rules to simplify, and the final postcondition we get essentially says that x equals y with a probability chosen by the adversary. So this program clearly does not uphold the property that the adversary can't guess the coin flip. And we can see also that this program does uphold the distributive law, because now we have the O+, the probabilistic choice happened first, clearly, from the kind of intermediate postcondition, and then afterwards we have the two non-deterministic choices. Okay, so in the paper we have some more involved examples. So one of them is this adversarial von Neumann trick program. The idea is it's based off the standard von Neumann trick, which was developed in the 50s. It's a protocol for simulating a fair coin, given a biased coin. And the way it works is basically that you flip the coin twice, and if you get heads, heads, or tails, tails, you try again. Otherwise, you can just output the first coin flip, whatever the result of the first coin flip was. And so here we modify this example a little bit, where instead of using a coin with fixed bias, the adversary is altering the bias on every round. And it can choose any bias it wants as long as it's between epsilon and 1 minus epsilon. So in the paper, we prove that not only does this program give us the coin is distributed uniformly, but also that this program almost surely terminates. So the adversary cannot force the program to go into an infinite loop with positive probability. And for that, we need some more rules. So here I have a very simplified version of our almost sure termination rule for reasoning about loops, but it still demonstrates the basic idea. So we have a loop invariant P, just like you would use in standard Hoare logic. And then we have a rank. So the rank is just some expression that's derived from the program state. And so as long as the loop body upholds the loop invariant and the rank strictly decreases with probability at least P, then we know that the guard of the loop will eventually become false with probability 1. And so the loop almost surely terminates. Now, this rule is inspired by some rules from weakest pre-expectation calculi, but in the paper we have some more advanced rules that allow us not only to show almost sure termination, but also to do so while reasoning about multiple outcomes at the same time. And so that allows us to prove specifications like the one you see here, where we say in any execution, so the precondition is true, we get a fair coin flip, but also the program terminates with probability 1. And so notably, we have two outcomes in the postcondition. So we're specifying a distribution of results, not just a single one. Okay, great. So in this paper, we talked a little bit about language where you have you have probabilistic choice, but you also have non-deterministic choices. But the non-deterministic choices are happening in a very controlled local way. And so if you were at the VMKI keynote the other day, you'll know that where we're trying to go with this is into a scenario where the non-determinism is arising from concurrent scheduling. And so this is a much more complicated scenario, because whereas in the language that we had in this paper, the non-determinism is very localized and controlled. In a concurrent execution, the adversary can make choices at every step of the execution. So there's a lot more non-deterministic blowup. And so here in this paper, we've developed a logic for probabilistic concurrency with some nice proof rules. We have support for unbounded looping, and it's all based on a compositional semantics. When we add concurrency into the picture, things get a lot more complicated. But in the last 6 months since we submitted this paper, we've actually made a lot of progress. So we have a logic with nice proof rules and concurrency, but no unbounded loops. And we also have semantics with unbounded loops, but no proof rules yet, no logic yet. And so we're slowly closing into the center of this diagram, and hopefully at POPL next year I'll be talking to you about it. Okay, so to sum up, we've developed a logic for reasoning about the distributions of outcomes in programs that are both randomized and non-deterministic. Part of the design of this logic involved coming up with propositional reasoning rules that mirror the typical equational laws of probabilistic concurrency that are common in the convex power sets literature. We've also developed rules for almost sure termination and a variety of other rules for reasoning about programs. And of course, where we're going next is we want to extend to concurrency. And so with that, I'm happy to take questions.
Patrick gets the first question this time. We have plenty of time for questions.
At some point, you mentioned the non-deterministic source and the stepwise, but you don't already have this problem in loop, because in the loop I can make a non-deterministic choice between either probabilistic choice or another one, iterating this. You don't have this problem?
Sorry, could you repeat? I didn't completely understand.
You said I will move to the two-bar stuff, which was non-deterministic choice at each step.
Oh, yes. Well,
so you don't have this problem with loop where you can make non-deterministic choice at each iteration?
No, you certainly can do that. So you can have non-determinism inside the body of the loop. And in fact, some of our examples do have that. What I meant by there's non-deterministic choices at each step is you may have a lot of threads executing at the same time. And so at every moment of the program, the scheduler is choosing which one to advance. So there's more non-determinism, or it's easy to have a lot of non-determinism. And you need more advanced techniques to reason about it in a compositional way. So for example, here we didn't have any separation logic, but in order to reason about concurrent loops, separation logic helps a lot.
Oh, go ahead. Give John.
Really interesting work, thanks. I'm curious about the intuition behind your loop rule in the von Neumann example. So what I was surprised by is that it says that, what I see this as saying is that the rank has to go down with high probability. Presumably P is a high probability. But what if when it doesn't go down, it goes up by a very large amount? It seems like this could lead to not terminating high probability.
Yeah, so I mentioned that this rule is very simplified. So there are a few extra constraints. The first thing, though, is that P only has to be non-zero, so it doesn't have to be high probability. But the rank, well, one thing that's not said here is that when the rank reaches 0, it must imply that E is false. Okay,
right,
so
that's standard.
Yeah, that's standard. The other thing is that it's integer valued. So strictly decreasing means decreasing by at least 1 on every step. And the third restriction is that it's bounded. So there's an upper bound. So if the rank may be bounded between, let's say, 0 and 10. And so in that scenario, it's actually enough to decrease with non-zero probability. It's a little bit unintuitive, but there's an argument based on Markov decision processes that it's kind of like well known in the weakest pre-expectation literature that this works. But it is limited because in a lot of systems you won't have bounded rank. So we do have some more advanced rules that don't rely on the rank being bounded. Whereas if the rank is not, if there's no upper bound on the rank, then things are a lot more complicated. And then, as you mentioned, if you have a high probability of increasing, then you get messed up.
Not so much a high probability of increasing, but a high probability of increasing by more than the probability of decreasing.
Exactly, but the main idea is that since there's an upper bound on the rank, there's only so much you can increase it by. So
Okay.
that's
I'll take
what
it
kind of
offline.
saves
Thank
you.
you.
Yeah, okay, sounds good.
One more question for Thibaut back there.
Thanks, that's a great talk. I was wondering, so you say the unsound but intuitive rule about the compositional rule about non-determinism is unsound because of the distributive law. Could you imagine having a different interpretation where you don't care about the distributive law and then this rule is actually sound?
Possibly. The issue is that when you do things like that, it's very easy to make the semantics non-compositional. And so you may invalidate, for example, the sequential composition rule here, the standard one. And if you don't have a sequential composition rule, your logic is basically useless. So it's possible there are other ways to do it, but this way is somewhat standard.
Okay, all right, let's thank Dome.
All right, now you can hear me. So please be seated. It's about time to start the first concurrency session of POPL. The first talk is going to be given by Aina Lynn Georges, called Data Race Freedom a la Mode. This is one of the recipients of a distinguished paper award this year. So the stage is yours.
All right, thank you so much. Hi, everyone. Thank you for coming. My name is Aina, and today I'll be presenting our work on bringing data race freedom to OCaml. This has been joint work with a number of great collaborators from MPI, Jane Street, and INRIA. So I think a lot of us here can agree that Rust is great. On the one hand, its powerful ownership type system provides fine-grained control over data, layout, and memory management. While on the other hand, it remains memory safe, and it even prevents data races. Now, that being said, unfortunately, not everyone wants to program in Rust. So why is that? Well, it might be because of its lower-level style of programming. It can sometimes also be slightly annoying to fight with a borrow checker. And finally, it has a somewhat steep learning curve for programmers that are accustomed to automatic memory management, such as a garbage collector. So the first question we ask is, can we bring the benefits of Rust to a higher-level managed language like OCaml? And this question was tackled by Anton Lorenzen and others in this ICFP paper from last year titled Oxidizing OCaml with Modal Memory Management. And I will henceforth refer to this work as OxCaml. Okay, so OxCaml brings the following features to OCaml, namely stack allocation, meaning the programmer can control where some memory is allocated, and memory reuse, which allows programmers to reuse some memory for a different purpose. And this design has been very successful. In fact, it has been implemented at Jane Street. It's getting ready for deployment. And this really goes to show that this design is not just theoretical. Okay? It can really be implemented at scale, and has been done so in OCaml. So let me give some overview of OxCaml, as it will provide the foundation for our work. So in OxCaml, type declarations and typing judgments are decorated with a mode. Okay, it looks as follows. What is a mode? Roughly speaking, a mode provides additional information that influences the interpretation of a type. Now, more concretely, it means that programmers can annotate their types with one of the modes, depicted here in 3 different lattices. And what's nice is that these modes can then be weakened towards the top element. So for example, a programmer can annotate a variable as unique, and then can then be weakened to alias. So all of these modes express something slightly different. So let's go through some examples. Right, so if x is marked as local, it means that x can only be used locally and may not escape a scope. If x is marked as unique, it exists uniquely and has not been aliased. And if x is marked as once, it can only be used once. For example, if x is a function, it can only be invoked that one time. So with these modes, OxCaml brings these features to OCaml. Okay, so it can use the local global axis to express stack allocation, and it uses aliased, unique, many once to express memory reuse. What's very impressive is that this design is completely backwards compatible. Okay, so that means that all existing OCaml code compiles, even with this new design, add the legacy mode, global many aliased. However, OxCaml does not consider concurrency. Okay, so we still have one nice feature from Rust that doesn't exist. And that's what we're going to do in this work. Okay, so we're going to expand the design of OxCaml to guarantee data race freedom in multi-core OCaml. And just like with OxCaml, we're going to remain backwards compatible. Okay, so more concretely, what would that look like? Let's see through an example what we will be able to do. Let's imagine we have a well-known OCaml data structure, a queue, that we want to share between 2 threads. Now, both of these threads will try to add an element to the queue, which will then create a data race since they're both trying to mutate it at the same time. So it's important that we protect the queue somehow. All right, so first step, well, let's imagine that we create some kind of lock, synchronization lock to wrap around the data structure. But the problem is this is still not enough. And the reason is, in languages like OCaml, you can freely alias any memory cell. So it's entirely possible to create this external alias y pointing to x, and thus circumventing the protections guaranteed by the lock. right, so at this point, I want to take a sidebar and discuss, well, how does Rust manage this? How does Rust guarantee database freedom? And it does so by adhering to the aliasing XOR mutability principle, which means that values can either be aliased or mutable, but never both. Okay, so is it solved? Can we do the same? Well, not quite. So the problem is the aliasing XOR mutability principle doesn't work well for data structures with internal aliasing. So to be a bit more precise, let's imagine we have a double-ended queue. Well, the internal implementation of it has a lot of aliases. So if we need to adhere to this principle, it essentially means the two threads cannot mutate it. Yeah. Okay, so in Rust, what can be done is, well, you can use some APIs that allow you to safely mutate concurrent data structures with internal aliasing, such as the GhostCell API presented in SFP'21. But the problem with APIs such as GhostCell, or the problem with GhostCell, is that it requires wrapping each node of this shared data structure with GhostCell wrappers. But that's not quite what we want. We want to share existing OCaml data structures cross-thread without having to re-implement them. All right, so the question is, how can we do this? And the key idea is going to, instead of using this principle, make this boundary around our queue a very harsh boundary, meaning we're going to create an encapsulated environment, which means no external aliases can exist, but we can do as many internal aliases as we want within the encapsulated region. So more concretely, what's our contributions? First, we present DRF-caml, a design that extends OxCaml to support concurrency. Now, DRF-caml statically prevents data races while remaining backwards compatible. However, it's going to be quite restrictive. So it also supports sharing existing OCaml data structures across threads. I'm going to explain how. And this whole design is proven sound in Rock and Iris. What are the key ideas with the design? First, DRF-caml guarantees data race freedom via two new mode axes called contention and portability. They are going to control how data can be shared across threads. Okay, next, DRF-caml supports mutation of shared data structures via two APIs, the capsule API and the reader-writer-lock API. And these are going to allow us to share existing data structures across threads without re-implementing them. Right, and I'm also happy to say that a design based on DRF-caml is actually also being rolled out at Jane Street. And in fact, you can all already play with it on an open repository. So let's get right to it. We are extending this, the mode axes with two new axes called contention and portability. And they're going to express how variables can be shared across threads. So to be more precise, if X is uncontended, it means it has not been shared between threads. If X is contended, it means it might have been shared across threads. And then for the next axis, if X is non-portable, it means it must not be shared across threads. While if it's portable, it can be shared across threads. Okay, now note I'm being very intentional with my use of verbs here. Okay, so there's a useful way to characterize these axes. The contention axis expresses something about the past of a variable. It expresses whether a variable has been shared, while the portability axis expresses something about the future. Can it be shared? Now let's see how these axes prevent data races. We're going to do this with an example. So we start out by allocating our queue, X. We then create a closure F that captures X and tries to mutate it. And we're going to run F in two different threads. Right, so first, I want to say, this program creates a data race. Right, two threads try to mutate X at the same time. So it's important that it's flagged as an error. And DRF-caml is going to do this with two rules. So first, mutable fields that are read from or written to must be uncontended. And second, functions that capture uncontended values are non-portable. Okay, so if we walk through this example, well, F is a function that captures X and mutates it. So X must be uncontended, the first rule. Thus, F is non-portable. But if we remember the rule for portability, if something is non-portable, you cannot share it across threads. Okay, so the error we get is that F is non-portable, but it's expected to be portable. All right, great. We have prevented data races. Now, problem. These rules are very restrictive. As you can see, with just this vanilla type system, you can't really share any mutable values across threads. Okay, so we need to fix this. And the answer is, we're going to present two APIs that will allow us to share mutable data structures across threads, the capsule API and the mutex API. Okay. And in the next couple of slides, I will present parts of both. First the capsule API, then the mutex API. Okay. So the capsule API really combines the full expressive power of both OxCaml and DRFCaml. It's going to use every mode accessed non-trivially. But simply put, a capsule is an encapsulated region associated with an abstract key type. Right? So let's see how keys are created. Keys are created by invoking key.create, where it creates this packed type. Okay, so a packed type is essentially OCaml's way of encoding existentials, so somewhat equivalent signatures like this, for those that are unfamiliar. Now note that key.create returns a key that's unique, and the uniqueness is also going to guarantee that it's fresh. Right. Now next, once a key is created, you can put data into the capsule by calling data.create. So data.create takes a constructor as an argument, and it creates data into any capsule. Now most importantly, this constructor must be a portable function. And this is crucial. Right? So if we remember, non-portable function or functions that capture mutable values must be non-portable. So that means if a function is portable, it does not capture mutable references. And what this really means is that by being portable, it's impossible to create external aliases. This is going to guarantee that the environment is truly encapsulated. Note, however, there are no other restrictions. Okay, so, and indeed, data.create can run in parallel in multiple threads. This is fine since we're adding new data into the capsule. But this would not be fine if we're mutating existing data within the capsule. Right, so let's see how that's done. It's going to be done via a function called data.map. And the idea is to mutate the contents of a capsule, you were going to need the key uniquely. Okay, so let's go through it step by step. The key is required uniquely to be able to mutate. We then take a map function, it must be portable again. We then have a data.t from this particular capsule, note the keys match. It then runs the function, returns the key uniquely, and the new data. Okay. So this is great. The uniqueness of the key will guarantee only one thread can mutate the capsule at any one time. However, what's missing now is the actual synchronization of the key. Right? We want multiple threads to get the key. And this is going to be handled by the mutex API. Note that in the paper, we present a more general reader-writer lock API, but for simplicity, I'm just going to stick to the mutex API. All right, so the key is going to be synchronized between threads with a mutex. To create a mutex, you consume the key uniquely. Right? So here the key goes into the mutex. And next, it can be acquired by calling mutex.protect. This works like a regular mutex acquiring as long as the function that you then run takes the key uniquely and returns it at the end. Okay. All right, this is all the ingredients we need. Let's use it in our example. So we're going to first create a key, put it into a mutex, and finally, we're going to allocate our queue by using data.create. Next, we're going to share this C between two threads, and they're going to run concurrently. And what's going to happen, they're both going to try to acquire the mutex. So let's, for example, say we are the second thread. They call mutex.protect. They happen to be able to acquire the key, which means they are now, the other thread is now waiting. They then call data.map to, with this unique key, to mutate the queue. And once they're done, they release K, and they relinquish it, and the mutex is closed. Now note that all of these functions, q.create, q.map, are really just mostly the original Q module from OCaml. Okay. The only difference, or the only obligation, is that the Q module must be annotated and recompiled so that all of the functions are portable. Okay, note that this is not a technical restriction. It's really like a key restriction here. It's very important that the queue doesn't create external aliases or anything that might break data rest freedom. Okay. However, if everything goes through, right, if the annotations go and the type checker works, well, nothing else needs to be done, and we did not need to be implemented. So in conclusion, I've presented DRF-Camel. It's an extension of OxCaml that guarantees data rest freedom with two new axes, contention and portability. I then presented two APIs, the capsule API and the mutex API, that will allow us to safely share data structures between threads. And finally, there's also a lot of things that I've omitted. So in the paper, you can also read about the full design. So in particular, I want to call attention to a mode that I didn't present here, part of the contention access that allows us to share, to read share between threads, so multiple concurrent readers. Of course, you can also get the complete APIs, the full presentation of the type system, and also details about the mechanized formalization in Rock and Iris. Okay. But for now, I'm very happy to take questions. Thank you.
Okay, we have a few questions. Let's start.
Hey, thanks for the talk. I was wondering if your key and data and mutex modules, are they typed by just, are you able to type them within your type system, or is magic involved?
No, the magic is involved, and part of the formalization is indeed to show that they are semantically type sound. Yeah, good question.
We have another question here.
Hi, this is really exciting work. I'm really curious if, so at the moment it seems like it probably doesn't affect the actual implementation of the language itself, it's more of just a type system feature. But I'm curious if you kind of along the way discovered opportunities to take advantage of this type system to improve the performance of concurrent code or parallel code that you might write with it.
So I cannot speak for the contention and portability per se. I know that the other modes did indeed, and part of the motivation was also to improve performance. So they actually influenced the backend of the compiler. As far as I know, portability and contention doesn't influence the implementation of the backend. The key focus was to guarantee data rest freedom for now.
Thank you.
It doesn't work.
Thank you. That was really nice work. So one question I've got is, how do you get data out of a capsule? So like you've got, say, a queue of integers, and it's in a capsule. Like, how do you get an int out of that?
Right. So you could destroy the capsule by consuming the key uniquely. This doesn't work if it's in the mutex, because it requires the key back. But if you could destroy everything, then yes, like if you could destroy the mutex and then destroy the key, then you can get data out. Yeah. But you can only get the data out that you're applying it to, right? And you could have like multiple views into your capsule, so you need to be a bit careful.
Okay, thank you.
Okay, we have time for one last question while I have the next speaker setting up, please.
Thank you. Thank you. So I was wondering, if I understood correctly, the mutex API is tied to this key type.
The one I presented,
which
yeah.
I find it at first a bit surprising. So is this a fundamental limitation, or could this be a mutex that wraps any type like we do it in Rust, or would that just not be useful for some reason in OCaml?
Oh, okay. This is a really good question. I think it deserves a longer answer, but the short answer, yes,
Happy
you
to
could.
chat later.
Yeah, but you could do a more general mutex API. Actually, the one we prove in the semantic soundness is slightly more general. But the problem is, because it requires something uniquely, and you don't necessarily have like deep uniqueness per se. If you have different nested references, you need to be a bit careful about which types you apply it to.
Okay, that makes sense. Thanks.
Okay, let's thank the speaker again. And the next talk is going to be given by Pavel Golovin on relinch, automatically checking linearizability under relaxed memory consistency.
Does it work? Yeah.
Okay, thank you for the introduction. And I would start my talk with just obvious fact that concurrent programming is quite challenging because software engineers should think about different aspects like synchronization between threads, safe memory reclamation, and performance. So usually they're using just concurrent libraries. For example, libcds, it's a concurrent library for C++. That is popular on GitHub and providing high-level primitives like concurrent queue, stack, set, and so on. And since it's so widely used, reasonable question is how we can be sure that such implementations are actually correct. For that, let's take a look on this example of usage concurrent queue. In the first thread, we are pushing value 1 and 2, and second thread, we are retrieving value from the stack. And which possible values we can see in second thread. So right answer is bottom, which is just a marker of empty queue, and 1. But we cannot see 2 or 42. Why it's like this? State-of-the-art notion of correctness for concurrent data structures is linearizability, which is saying that if implementation is linearizable, all its behavior should be explained by executing operations of the data structure in some linear order, which is respecting runtime order. So for example, we can first execute dequeue and see actually empty queue, and then execute enqueue1 and enqueue2. And since we should respect runtime order, we can execute enqueue2 first. This is two other linearizations that is showing that we can also get 1. 2 and 42 we cannot get, so they're considered incorrect. So far, so good, but it doesn't work well for weak memory model context, unfortunately. So here we have two data structures, queue and stack. In first thread, we are pushing value into stack and retrieving value from the queue. And in second thread, vice versa. Question is, can we actually see both of these structures empty in both threads? And it's counterintuitive, but under weak memory model, it's actually, it's not linearizable, definitely, because there is no linear order that could justify this output value. But this is intended behavior under weak memory model, because there is no reason to forbid this. There is no interaction between threads here, no passing data. And if we would forbid this behavior, we just introduce more penalty for performance. So we still want to have atomicity, but only per each object. So if we take a look only on operations on the stack, this is fine, because first we can execute pop and see empty marker, and then execute push. And same for queue. But just atomicity is not enough. Some implementation of concurrent data structures want to provide guarantees on synchronization. For example, here, it's very natural to expect that if in second thread we retrieve value 2 that was pushed in the first thread, and before stack was modified, we actually see non-empty stack in the second thread. So it's natural to expect here synchronization. So new notion, like notion of correctness that is suitable for weak memory model, it's atomicity per each object and preserving synchronization that is defined in that way. So it's suitable for this particular implementation depending on which, how strong guarantees it wants to provide. Problem is that there is no such automatic tool that can check this, this notion of correctness automatically. So we are providing a new tool, relinch, which is the first tool for checking relaxed linearizability of concurrent data structure fully automatically. It's based on model checking. It's automatically can explore tests of bounded size. It scales up to 7-9 operations. And we actually found violation in popular on GitHub library libcds. In the rest of my talk, I will answer how we answered on I will tell you how we answered on 2 questions. First is how to define such relaxed specification, and how then verify implementation against it. Let's start with first one. In the beginning, we just take standard implementation of queue for single thread that has infinite array of nodes, counter for beginning and end of the queue, and its standard way to make it linearizable, just wrap global lock around it. But problem that this global lock will introduce too much synchronization. It's actually expose synchronization between each pairs of method calls. Instead, we will use partial lock, which was introduced on POPL 2023, and this still ensures atomicity, but does not expose any synchronization to the client. This is artificial device that we cannot use for implementation, but it's very nice abstraction for defining specification of such relaxed data structures. So if we want to define somewhere synchronization, we actually can use C11 atomic accesses. On this example, you can see that we added acquire and release accesses to accessing elements of nodes array. And only operation enqueue and dequeue that is accessing same index in the array will have synchronization. And only their synchronization should be preserved by implementation. In other cases, for example, if we have a pair of 2 enqueues, no synchronization is expected. So this is how our specification looks like. Then let's try to verify implementation against it. And we split this question in 2. First, we will try to verify our implementation against one test, and then try to solve bigger problem, how to check exhaustively all possible tests. So for one given test, our algorithm looks like this. We have 2 phases, and first phase, we are analyzing specification. For that, we will run model checker on a given test with a specification and collect all behaviors that it exhibits. For example, we have this test client, and model checker will give us execution that is represented by, for example, it could be represented by execution graphs. And important things that is recorded, it's return values of methods and synchronizations that should be preserved by implementation. On the next phase, we will run model checker on the same test, but with implementation. And again, model checker is able to enumerate all possible executions of it. And for each execution, we are checking that there is at least one execution of the spec that match to this. It should have same return values and has less or equal synchronizations. So for example, this is one of execution graph of implementation that could be observed. And we see that there is actually behavior of the spec that have same values and preserve all synchronizations that it has also preserved by implementation. And it's important to allow implementation have more synchronization than it's in the spec. This is how we check one particular client, but how to check all of them, because of course checking just one is not enough. We just check this client, and we should also check this, and there's many more clients. So we can just try to run our tool on all of them, but it doesn't scale well, because number of clients that we have to check grows very fast with increasing number of calls of methods of data structure. Instead, we will try to do something smarter. We observed that this client in the top can see empty marker 1 and 2 values. And other clients can observe just some subset of these values. So we called this client in the beginning as the most parallel one. And other clients we will consider just as some extension of this most parallel client. So we can leverage this observation to running our tool on most parallel client and observe all possible executions of all extensions at once. But it doesn't work straightforwardly. For example, imagine that we have such implementation that have some bug, it's just trivial implementation that always return empty marker. If we just run our most parallel client on this implementation, we see empty marker, but it looks fine because we can justify this value by first executing dequeue. But if we run this implementation on the extension of most parallel client that forbid execute first dequeue, it's actually this extension reveals the bug. So conclusion that checking extensions of most parallel client is really necessary. We cannot avoid it. But we can still use most parallel client to explore all executions. And then for each output, we will calculate minimal set of extended client that render this output erroneous. And then we can use this information to actually check all behaviors of implementation that extended client that forbidding this output cannot observe it. So this is, now I show you how our final algorithm working. And first phase, we're analyzing specification. We're running model checker on most parallel client with the specification, collect all behaviors, and then for each output, we will calculate minimal set of extensions that forbid this output. How exactly we'll calculate this set, I'm inviting you to read in the paper. On the second phase, we are checking implementation, running model checker on the most parallel client with implementation, checking that each execution graph have some matching execution graph of the spec, and then we're checking that output of this implementation graph cannot be observed by the extension, by forbidding extension. So it makes it inconsistent. For example, this is a graph that could be observed by the implementation, buggy implementation that I was showing you before. We are adding this extension and checking. Check, is it still a consistent graph? If it's still consistent, so we found a bug that could be observed by this extended client. So in the end, how does it scale? On this chart, we can see time of checking most parallel client depending on size from 2 to 9. And first fact that we can see, oh yeah, it's for just for Michael Scott Q implementation. So we actually checked most parallel client of size 9 just in 15 minutes. And that means that we checked that our implementation is correct under any client that have less than 10 operations with any possible order between them that is forced by client. And also another fact that you can notice that time of enumerating of all executions of most parallel client is bigger than our additional checks of refinement that we introduced. So our additional checks are not bottleneck. So to sum up, what we learned today, we can use model checking for checking relaxed inusability of concurrent data structure automatically. We can use partial lock to expressively define specification for such relaxed data structures. We can use most parallel client to verify all clients at once. And this approach is feasible enough to check, to find violation in popular libraries like libcds. Thank you for your time and attention.
Okay, we have plenty of time for questions.
Hi, what was the bug that you found?
Yeah, I can show you. Thank you for your question. So it looks like this. It's some client where we have some output which cannot be explained by any linear order. But in the documentation, they say that this data structure is linearizable.
Thanks.
Okay, we have another question on this end.
I just have a question about the semantic of your partial lock.
Sir, can you repeat?
Can you? Okay.
Yeah.
I had a question about the semantic of the partial lock, because the way you presented it, it was just like this block is atomic, but then it can be reordered with other instance of the same partial lock. But if you do that, you seem to still expect that if you do multiple calls to the same object that are bounded by partial lock, they cannot be reordered.
Yeah.
So does that mean that you still have a concept of program order between partial locks?
So yeah. So question is what is exactly semantic of partial lock? This partial lock introduced synchronization that can be seen only by library events. But it's not exposing any synchronization outside.
Okay, so yeah, so that means that multiple partial lock from the same library will be synchronized, but not with the others.
I mean, yeah, they're synchronized, but only for from the point of view events of library. Yeah. That is used for implementation of data structure.
Okay.
Other questions? If not, let's thank the speaker again.
Thank you.
So the next talk is pre-recorded. It's going to be given by Evgeny Moisenko, called Relaxed Memory Concurrency Re-Executed. It is also a paper that received a distinguished award in this POPL. I believe Evgeny will be live with us after the talk for questions.
Hello, my name is Evgeny. And I'm going to present our paper, Relaxed Memory Concurrency Re-Executed. So first of all, let me briefly introduce the topic. A memory model of a programming language defines what values reads from shared variables can observe in a concurrent program. A memory model is called relaxed if it permits non-sequentially consistent outcomes, that is, outcomes that cannot be obtained as a result of simple interleaving of instructions from different threads. Such outcomes can typically arise as a result of some optimizations performed by the compiler or the hardware. So for instance, if we take a look at the program shown on the slide, we can notice that an optimizing compiler can reorder two independent instructions in the left thread. After this, the outcome where a equals b equals 1 can be obtained as a result of interleaving of instructions. It means that this outcome is an allowed relaxed outcome of the original program. Defining a relaxed memory model has been a long-standing challenge because it must balance two conflicting requirements, performance and programmability. For performance, the model should be weak enough to support all the desired optimizations. However, if the model is too weak, it can accidentally allow so-called thin air values. So if we take a look at another program shown on the slide, we can see that an outcome where a equals b equals 0 is a valid outcome of this program. On the other hand, an outcome where a equals b equals 1 is a thin air outcome because no reasonable compiler optimization can enable this outcome. Yet, the current formulation of the C-memory model called C20 technically allows this outcome. So the C20 model has this thin air values problem. In order to forbid thin air values, researchers propose to strengthen the model. The resulting model is called RC20. But it turns out this model is too strong because, unlike C20, it does not support optimal compilation mappings to hardware, and it does not support all the desired local program transformations. To see why it happens, we need to have a deeper look at the details of these models. Relaxed memory models are defined in axiomatic style axiomatically in pre-execution style using so-called execution graphs. Nodes of this graph represent various events such as read or write accesses to the memory, and the edges in these graphs form various relationships between these events. Most notably, gray-colored program order edges represent syntactic order between the events, whereas green-colored reads from edges connect each read event to a single write event from which it takes its value. Semantics of the program is defined as a set of execution graphs, and the memory model defines what execution graphs are consistent. So, going back to the examples, if we consider a program on the left and all its possible execution graphs, the C20 memory model considers all of them consistent. On the other hand, the RC20 model considers only the left graph as consistent. That is because RC20 is basically C20 consistency plus an additional constraint requiring that the union of program order and reads from relations should be acyclic. But it turns out that this additional constraint is too strong, because if we take a look at the program on the left and consider all of its possible execution graphs, then again C20 considers all of them consistent, but RC20 considers only two of them on the left consistent. However, in this case it poses a problem, because this third cyclic execution graph actually corresponds to a valid outcome that can be obtained as a result of instruction reloading. Can we prevent thin air outcomes while maintaining compilation efficiency? In our paper, we address this challenge by proposing a novel memory model called XMM. XMM eliminates thin air outcomes while supporting efficient compilation and local program transformations, such as instruction reloadings and instruction eliminations. As such, the first contribution of our paper is a novel axiomatic operational semantic framework for relaxed memory models, XMM. The XMM framework builds on a given axiomatic per-execution memory model. It extends the given memory model with out-of-order re-execution capabilities, enabling efficient compilation while forbidding thin air outcomes. We instantiated the XMM framework with the C20 consistency constraints to arrive at the model, which we call XC20. Next, let me explain how XMM works using some examples. The XMM has two operational rules to construct execution graphs. The in-order execute rule at each step adds one program order and reads from maximal event to the graph, and it ensures that the resulting graph remains consistent. Whenever a read event is added, it must be connected to an existing write event via reads from relation in order to prevent thin air reads. However, the execute rule alone cannot create cyclic graphs. This is why we need another rule. The out-of-order re-execution rule enables creation of cyclic graphs. It works as follows. Given an already constructed graph, it selects a subset of committed events of this graph, and then it rebuilds the graph while preserving the committed events. Similar to the execute rule, it ensures that the resulting graph remains consistent. Importantly, during the re-execution, it is allowed to add a read event that reads from nowhere, but only as long as it is committed. This constraint prevents thin air reads by ensuring that the values of committed reads are grounded by the original execution, and the writes from which they read from are guaranteed to be restored in the resulting graph. With the help of these two graph construction rules, XMM achieves no thin air, optimality of compilation mappings, and soundness of local program transformations. However, we must admit that XMM is not the first model that attempted to fix the thin air values problem. In fact, XMM was inspired by the Java memory model that was based on similar ideas. However, our model avoids the pitfalls of JMM in supporting desired optimizations. Previously, the research community also proposed the operational premising semantics, the VGSTMO model based on event structures, as well as some other notable models, which we do not mention on this slide due to time and space limitations. These models are commonly referred to as multi-execution memory models, and they also avoid thin error values while supporting desired compilation properties. So what makes the XMM model stand out? To answer to this question, we need to look at another important program transformation, thread sequentialization. Sequentialization merges two threads into one. Let us look at some example. Firstly, in this example, the second thread can be merged into the first thread. After this, following the conditional assignment to variable x, the read from x in the last statement always returns 1. Next, the assignment to variable 1 can be reordered above. In the resulting program, an interleaving where instructions of the second thread are executed in between instructions of the first thread leads to a relaxed outcome where a equals 1. Thread sequentialization is sound in C20 and RC20 models. However, it is unsound in the multi-execution memory models. In XMM, we fix this problem, and in our model, thread sequentialization is also a sound transformation. This is the second notable contribution of our paper, as XMM is the first model to support thread sequentialization along with other desired properties. To showcase how exactly XMM supports thread sequentialization, let us go back to the example. The key here is that, unlike previously proposed multi-execution memory models that allow execution of only a single thread at a time, XMM allows execution of several threads. The only requirement is that threads should be re-executed one by one in accordance with a chosen thread ordering. So, to justify the relaxed outcome where a equals 1 for the given program, XMM first constructs an acyclic graph shown on the slide. It then commits events E4, E5, and E6. After this, it re-executes the program, constructing another graph. Construction starts by adding events E5 and E6 prime, and then it proceeds to re-executing first and second thread one by one, in accordance with the thread sequentialization ordering. So in this way, XMM supports the thread sequentialization transformation. XMC has another advantage over previously proposed multi-execution memory models. It is amenable to automated reasoning in the form of model checking. So first, let us have a look at the situation with other models. Sin20 is basically not checkable because of the thin error reads problem. On the other hand, the problem of model checking under RC20 is relatively well studied, and there exist a lot of tools. But these tools rely on the acyclicity of execution graphs. The problem of model checking under multi-execution memory models was untackled until very recently. A tool was proposed for the VGSTMO memory model, however, it was not proven sound. So the third contribution of our paper is that we developed XMC, a sound model checker for the XC20 memory model, and we proved its soundness. XMC was developed on top of the state-of-the-art GNMC tool. Given a program, GNMC explores all its RC20 consistent executions. To construct these executions, GNMC relies on a procedure resembling the execute rule of the XMM semantics. At each step, it adds single maximal event and checks that the new execution graph remains consistent. Thus, to generate cyclic executions, the challenge was to extend GNMC with a procedure implementing the re-execute rule. However, in its general form, the re-execute rule exhibits significant non-determinism. It can be applied at any step with an arbitrarily chosen set of committed events. To tame this non-determinism, we have developed a strategy that implements a restricted version of the re-execute rule, making the model checking tractable in practice. To this end, we use a heuristic based on load buffering races, specific read-write races, with a program order and reads from path from a read to a write event. When a load buffering race is detected, the algorithm deterministically identifies committed events, and then it performs re-execution. In our paper, we show that XMC works reasonably well in practice and is capable of verifying realistic benchmarks, in some cases with the performance comparable to the baseline GNMC model checker. We refer to our paper for a more detailed evaluation. So in our paper, we have proposed XMM, a novel semantic framework for relaxed concurrency. Unlike its predecessors, XMM is defined in almost a pure execution style, making it potentially easier to integrate with existing specifications. For example, the C language specification, which is also given in a pure execution style. Moreover, XMM is the first model of its class that supports thread sequentialization transformation in combination with local program transformations, such as instruction rewording and instruction elimination. And finally, XMM is also amenable to automated reasoning. Yet there is still much work to be done. First of all, we are currently working on the work mechanization, and we have already proved some of the model's properties in this proof assistant. Next, we are planning to support sequentially consistent accesses in the model as standalone primitives to support the full range of the C language features. And finally, we aim to achieve completeness of the model checking algorithm and to prove it formally. So to conclude, XMM is a novel semantic operational semantic framework for relaxed concurrency. It solves the thin error values problem, supports optimal compilation mappings to hardware, local program transformations, and sequentialization transformation. Moreover, it is amenable to automated reasoning in the form of the model checking. Thank you, and I'll be happy to answer your questions.
Okay, we have plenty of time for questions. Is Evgeny with us live? Student volunteers? We have. Okay. One, two, yes. Yeah, one, two.
Yes, hello, can you hear me?
Yes, can you? Who has a question? I saw a hand raised earlier.
Hello, Evgeny, it's Victor here. It's a
Hi.
very nice piece of work. I would like to ask you, what is the main difference between your model and the Java memory model, which also has this re-execution idea?
Yeah, okay. Sorry, I know.
I'll repeat the question, maybe it's not audible. So the Java memory model of Manson and other had the similar idea of committing some events and adding some more and some more. So what is the main difference that makes your model work and the JMM not work?
Yeah, sorry, I didn't hear out because I have an echo. Let me.
One more time.
Can you hear me?
Yes. What is the difference between your model and the Java memory model? In the sense, the Java memory model has a similar strategy as yours, but somehow the Java is broken and yours is okay.
Yeah, can you hear me? Because I think there's some technical problem.
We can hear you.
I mean, I heard the question, but when I start speaking, I also.
Yes, we can hear you.
Okay. Yeah, just when I start speaking, I hear myself. So okay, I'm going. So the question was, what's the difference with the Java memory model, which is based on similar ideas? I think the differences, like, yeah, as I said, the idea is similar, but the difference, there's a lot of like technical differences in a way how we commit the events, for example, and what's the rules of the committing events. So, for instance, in one of the most significant differences in the Java is that whenever they commit events, the committed events, like they are preserved through whole construction of the graph. Like once you commit an event, it's always committed. Like you cannot make one re-execution step with one set of committed events and then make another with another committed events, because like the committed events must be grow monotonically in Java memory model. We also tried this at first in our model, but we realized that this doing this naively doesn't work. So we had more relaxed rule, like we allow basically dropping committed events in terms of Java. And there were also a lot of other technical differences with respect to what constraints we put on committed events. So for example, one of the issues with Java was that they were requiring that the program order between the committed events should be preserved, but it is too strong for reordering. And that's, for example, we have a more relaxed constraint when instead of program order, we use a special subset of program order, which we call relaxed program order, that basically only the program order that is enforced by fences and release, acquire release events. So it's really hard to answer the question without going into too much detail. So yeah, but basically the answer is that there's a lot of technical details in how we handle committed events.
Okay, thanks. Any other questions? So I have one, if you can hear me. So when you talk about soundness and completeness of your model checker, how do you define that? Is that with respect to bug finding or with respect to the executions that you explore? What does soundness mean?
Our terminology is in terms of executions we explore. So by soundness, we mean that every execution graph that we generate is XC20 consistent. Yeah, so that's, and in this sense, yeah, we do not claim completeness because basically, yeah, we do not know if it is complete, if it is possible to enumerate any consistent graph. It's actually quite complicated problem.
And in the same context, is there any notion of minimality in your exploration, or could you be exploring the same execution multiple times?
No, unfortunately, there is also no minimality here. Unlike basic GenMC algorithm, which guarantees minimality for RC20. Again, because of this cyclic execution graphs, the problem becomes much more complicated, and we do not know yet any way how to kind of ensure minimality, or even if it's possible.
All right, thank you. Any last questions? No? Okay, so let's thank Evgeny live.
Thank you for having me.
And I have the last speaker set up. So the last talk for today is going to be given by Iason Marmanis, titled Model Checking C, C++ with Mixed-Sized Accesses.
Hi, okay, can you hear me? Perfect. Hi, I'm Iason, and today I will present our work on model checking concurrent programs that use mixed-size accesses. This is joint work with Michalis Kologiannakis and Victor Vafiadis. So as you know, concurrency is when you have a number of threads, and these threads interact with each other. And for example, with shared memory concurrency, they read and write on the same variable. And concurrency is in general hard to reason because of the non-determined is induced by the scheduling. So at each point, you don't know which thread is gonna run. And also, it can get even worse because of weak memory behaviors. So you cannot really reason by interleavings of threads. But it's very important to be able to reason about concurrent software because this is used by critical software, for example, by operating systems such as the Linux kernel. And let me show you an example from the Linux kernel of a data structure that you would like to be able to verify and reason about. And this is the lockref. It's a reference counter. So it's pretty much a lock with a counter that you increase. And on the left, you can see how is the data structure. So it's pretty much a union of two things. It's either 8 bytes, an 8 bytes variable, 64 bits of a log count, along with a structure that is it's 2 variables of 4 bytes, a log and a count. So for anyone who doesn't know, union is like the same data you can see it in 2 different ways, either 8 bytes or 2 times 4 bytes. And on the right, you can see a method that is increasing the reference counter. And what this does pretty much in the first part with the yellow is the fast path. So it's trying to read the whole thing as 8 bytes. And if it sees that the log part is not taken, it's trying to increase the counter at once with this cas comparison operation. And if it does so perfect, it returns nothing else to do. Otherwise, it's falling back to the slow path. So it's trying to take the log, so access just the log part of the 8 bytes, so only 4 of them, then increase the counter, so access the other 4 bytes, and then again access the log by releasing it. And this pattern here is called mixed size accesses. So you're accessing the same 8 bytes in different ways, either the whole thing or the first 4 bytes or the other 4 bytes. So to verify in general concurrent programs, one such technique would be stateless model checking. And it's good because it handles concurrency, it is automated, and it also handles weak memory behaviors. But unfortunately, you cannot use it right now to verify a program such as the previous one because it cannot handle mixed size accesses. So our contribution is Mixer, a stateless model checking algorithm that handles mixed size accesses. It's complete, so it explores every behavior that the program can give you. It's optimal. I'll discuss more about what this means later. It only uses polynomial space, so it's really stateless. And we also have a tool implementation that we use to verify some clients of the lockref data structure. So before going to the problem, I need to give you some background on stateless model checking. So as I mentioned before, it's an exhaustive exploration. It's trying to, you give it a concurrent program, it's trying to explore every trace that the program can give you. And as an example, you have this program here with 3 threads. The first one is writing 1 to x, the second is writing 1 to y, the third thread is just reading x. And stateless model checking would give you the 3 factorial, the 6 traces that you get. But of course, this doesn't scale. As you can see, it's the state space explosion problem. The more you increase the size of the program, the more exponentially the number of traces increases. So stateless model checking is usually combined with a technique called dynamic partial reduction, or DPOR. And what this does is it's based on the observation that instructions often commute and you don't really need to consider every trace. The state of the art, instead of actually exploring traces themselves, it explores partially ordered traces. So only the orderings that are really necessary. And these are called execution graphs in the literature. So here you can see the 2 graphs that this program corresponds to, and they only differ in what the read reads from. So the middle thread, it's immaterial, so you don't need to order it with anything. So just to see how the execution graphs look, you might have heard from the talk before, but let me repeat. So it's a graph. It consists of a set of nodes. Each node corresponds to an instruction. So the write 1 to x corresponds to this write x1 node here. And with the green node, with the green arrow here, the arrow, it's just the order where it's just an order that says where does the read from. So on the bottom, it reads from the leftmost node. It reads 1. And I'm assuming the initial value of 0, so I'm omitting any edges that come from the initial values from the initial write. So how does the state-of-the-art DPOR work? How does it explore these execution graphs? So it does so incrementally. So again, with the same program, I'll show you a simple run. It starts with the empty graph, then it executes the leftmost instruction. This is random, but I'm assuming every time that you execute the leftmost thing that exists. So you're adding the right, then you're adding the second right, so you're in the third graph here, and now you have two choices. DPOR has two choices. You're adding a read, it can either read 0 or it can read 1. So it will branch out and give you the two execution graphs, and that's perfect. So let me show you, make it a tiny bit more complicated to show you another feature of DPOR that's very important. It's the same program on the bottom, I'm just moving the first instruction at the end. So the right 1 to X goes at the end. So again, you execute the two first instructions. Now the read can only read 0, nothing to do. And here you're about to execute the right 1 to X. Now you again have two choices. Either just execute it, do nothing else, and this is the top execution graph that you see, or add it and revisit the previous read. So you need to give the read the choice to read from a write that was added later. And you can see this with the edge there. Now the read is reading from the later write. This is called the revisit. It's very important how DPOR works. Two more things about DPOR that I want to mention is that you in general want to only explore consistent executions. So in general, you can create execution graphs that don't really make much sense. They might have some cycle that's prohibited. If you're assuming sequential consistency, there is no trace that can explain it. So there is a consistency predicate that tells you whether a graph makes sense or not, and you care about it. And another thing you want from these algorithms is to be optimal, which means that you're not getting any graph more than once. You get exactly the two graphs that, in this example, you get exactly two graphs, no more. And one key assumption for DPR to work that I want to mention will be useful very soon is extensibility, which says that given a graph that you have reached and the graph is consistent, and in one more instruction that you could have executed, so one pending instruction, there is a way to add the instruction to the partially ordered trace and remain consistent. Small example, one thread, two instructions, write 1 to X, read X. You have the execution graph with just the write. Well, you can add the read and make the read 1. That's consistent, perfect. But you could have also added to read 0, but this is not consistent. So any coherent model will tell you that this doesn't make sense. So this is not consistent. All right, now I'm almost getting to the problem. Why it's not trivial? What's the problem with mixed size access and DPOR? So how would you do it? So the first thing you would have thought would be to take the mixed size access, break it into multiple accesses. So the lock and the ref lock, the 8 bytes access, break it into 2. Or here the 2 byte accesses of that. So this is an instruction that just writes 1 and 1 to both bytes of X. X has 2 bytes. So you could just break it into 2 accesses, write to the first byte, write to the second byte. But unfortunately, this doesn't work. And the problem is that you're creating executions that are not extensible. So take this program, for example, 2 threads. The first one is writing 2 to the first byte of X, and then reading the second byte. And the second thread is the instruction on the top, just writes 1 to both bytes. So DPOR would end up in the execution that you see here, where the rightmost write is ordered before the write on the left. This is with this big edge here on top. And pretty much what this means is that the access of the second thread is ordered before both instructions of the first thread. This is consistent, fine, but there is no way to complete the graph, to complete the execution and add the second access. And to see why, in the first graph, you're pretty much ordering the second thread before everything. So now you cannot add the write 1 to the second byte because the read must have read 1, not 0. So extensibility breaks and DPR fundamentally doesn't work because of this reason. So our solution Mixer works under the following observation, is that yes, you don't have extensibility in the access level, but you can still assume extensibility at the instruction level. So what this means is that if you're not executing instructions half, like some accesses, you can fully execute one instruction. at each point. So before you would have executed the first thread only, and now you can one thing you can do is just add the missing instruction at the order after the first thread. And this means that the first graph is extensible. Fine, but this is not so simple, unfortunately. And you can see this with a very simple example. 3 threads. The first thread is reading both bytes of variable x. The second thread is writing 1 to the first byte. The third thread is writing 1 to the second byte. And the question is how to read the execution, whether the read reads 1 for both. And you would assume that you would get there by, again, if you think that you're executing the program left to right, you would just add the read, then add the second write, do a revisit, make it read from this write, and then do one more. And you would think you would get there, but actually you don't. What you get is the execution where the read only reads from the rightmost write. And the reason for this is how this kind of DPR algorithms work. So what they do when you revisit is that you remove all the events, all the nodes that were added after the read and are not the write or something that the write depends on. So they would get you to the execution there, which is not what you want. And going forward, you also cannot reach the graph that you want, so you would miss it. Our solution to this is a new kind of revisit, procedure called that we named the multi-write revisits. So when you're revisiting a read from a write, you also have the choice to have a set of writes, the keep set, that it would have normally been removed from the execution because of how DPR works, but you actually don't. So here, from the execution where the read reads from the middle write, you have the choice to take one revisit step, and keep the middle write, so don't remove it. And they together, with the write that you're about to add, revisit the first read, and you get the execution that you want. Fine. This adds a lot of more things that the algorithm can do, so a lot more execution graphs. And there comes a problem, how do you know you're still optimal? So this is the whole difficulty. And to see why, how could this happen, consider another execution that the DPOR would reach, which is the read reading from only the rightmost write. And here you would again do the exact symmetric thing. Add the middle write, keep the other write, revisit together, get the same execution. So your algorithm wouldn't be optimal anymore. So for this, we need a bunch of conditions that we've added, and one of them is tie breaking. So tie breaking would just, it has a way to tell which of the revisit steps of these two you allow, and we also have some more conditions to guarantee that to do a revisit, there is a unique choice of keep sets that are allowed to do it. So this is how we guarantee optimality. Okay, so moving on to the evaluation, we implemented a mixer on top of an open source tool, GenMC, and we used it to verify clients of the Lockrev implementation from the Linux kernel. And here we have one parametric client that is parametric to the number of threads, and we managed to run the tool to verify it for up to 4 threads before timing out at 30 minutes. And the reason for this is, as you can see, the executions grow very fast, from some to hundreds to tens of thousands. And finally, we also observe that when running Mixer to benchmarks that do not use mix size access, you're only introducing some moderate overhead over the state of the art, so a bit less than ×2. And just to recap, I presented Mixer, a DPR that handles mix size accesses. It's complete optimal, it uses polynomial space. It does so by a new kind of revisits that we introduced, the multi-write revisits. And in the paper, you can see a sketch of how you would extend this algorithmic framework to support a larger class of programs, so transactional programs. So mixed size access, you can see them as a transaction that does all the accesses with some atomic semantics. And that's all I had. Thank you very much.
Any questions? Okay, let's start here.
Hi. So can you go back to the slide where you explained the keep sets? Yeah. So am I missing something? But these, why does this not happen? Because they are unique. These are not the same. the case.
So, sorry, could you repeat it? Why they
So
are the same?
why is the second one? Why does the second one not happen? Why do you have optimality? You say that you need to have unique K for each revisit, but these are unique. These are different.
Yes, so there are two conditions. Type breaking and being unique, which is a bunch of conditions I don't have space to add. So type breaking works in the following way. First, you force the scheduler to only execute left to right, and then only allow keepsets that are on the left of the final write that does the revisit. So that's why you allow the top revisit, but not the second. Thank you.
Over here.
I've been thinking about similar stuff, and I was wondering because one of the ideas I had.
Sorry, can you?
Okay, sorry. I was thinking about similar stuff, and one of the idea I had was to keep the writes together but break up the reads. Is it a technique that you have considered, or not?
So I think the problem with that, and many of the problems that you would get, is with the read modified write operations. So I don't think this would help at this point. So even if you split the reads, as soon as you've added the reads in some way, they're ordered before some instruction that is a read. Imagine, like similar to here. So imagine that the second thread here, just this NRMW, it reads something that forces it to be before the leftmost read. You cannot close RMW, and this wouldn't matter if split the write or don't split it. Does it make sense?
Not completely, but maybe we can talk.
Maybe I can chat on and write you the example.
Hi, I'm a bit confused about which memory model you've been using, because as far as I understand, it's undefined behavior in C++ to do mixed-sized accesses, because you would have to do nasty casts that violate the object model. So how can I don't think you can even write code that would do this. I mean, the Linux kernel does their own weird stuff, which is not the actual C++ memory model. But outside of that?
Yes, it is undefined behavior. We're assuming some release acquire, but the framework in general is parametric to the memory model. I didn't want to discuss about it. I'm assuming a C here. But so you can use it for your memory model that you have at hand, supposedly that you have some semantics, like it's not undefined behavior. So you could have used it for the Linux kernel.
Okay, I'll ask now, more later, thanks.
Any other question? So maybe I have a small one or a couple of small questions. I remember seeing another paper in the last year or two, I believe in Atlas, kind of targeting mixed-sized accesses, even building on top of GenMC, I think. Is this in your radar? Can you compare your technique to that?
I know about so they discuss a lot about the implementation part. As far as I understand the paper, they don't change anything else, so they should have hit some counterexamples that we have. So I'm not completely sure that I understand correctly, but if they haven't changed anything significantly, probably they would have hit some bug. But
okay. And then
but maybe I don't understand it completely, so I don't want to say much.
And here you said you assumed a C axis on the independent kind of bytes?
In the presentation, yes.
In the presentation.
The implementation is some release acquire plus RMWs.
I see, okay. And are you enumerating RFs or RFs NMOs?
RF-NMO.
RF-NMO.
Yeah.
And do you expect the consistency equation for RF to become any more difficult now with these mixed-sized accesses for release acquires?
Like if you don't have MO.
Yeah. So normally it's an easy problem to solve computationally for release acquire. But now that you have these multiple RF edges, does it make the problem any more difficult?
I haven't thought about it, honestly, so
Okay.
I'm not sure.
All right. Any last questions? Okay, let's thank Yasin again.
I can introduce myself.
No, it's my
I'm
job.
the chair now.
No, it's my job.
Okay,
nice. So, okay, so it's almost the time. Let's thank you for coming to this afternoon session. This session is about cleaning algebra with tests, and let's welcome Chen for the first talk, CFG-CAT, efficient validation of control flow transformations. Okay.
Hi. So I'm Chen, I'm from UCL, and this work is mainly done when I was in Boston University. And today I'm going to talk to you about CFG-CAT and control flow validations. Did it work? Yes, nice. So the story starts with legacy applications. And in our digital life, there are some legacy applications that are sprinkled around our digital infrastructure. And a lot of them are unsupported. They won't get updates. And they are in binary form, so people cannot read it. And they are rare. Sometimes they are rarely used, so they don't receive the testing that they need. So typically, the way that we deal with legacy software is try to understand it to make sure that there is no problem with it, or we try to rewrite it using like modern software, or we even can verify it. But all of these requires to decompile the binary into a readable language, and then it will help us to understand, rewrite, and run like state-of-the-art verifier on it. So this raises a problem of the correctness of the decompilation process. And in this work, we are focusing on one particular stage and one particularly complicated stage of decompilation called control flow restructuring. And control flow restructuring is basically the process of turning a control flow graph or a go-to program into a program with while loops and the normal programming feature that we can actually read. So this is a very active research area, and people are continuing to output algorithms, new implementations here. And this is one screenshot from a paper at USNIX, and there's a little 4 here that was supposed to show but covered. So this is 2024, so it's very, very recent. So as we can see, this is an ever-developing field. And for this work, we don't want to design a validator for the decompiler of yesterday. We want a generic algorithm that can work for the decompiler of tomorrow. And we want it to be powerful. We want it to not produce false results, both false positive and false negative. And that's a very big goal, and it can only be achieved by understanding what are the properties that they want to satisfy. And finally, we want this to be automated and very efficient so that we can put this in decompiler and the programmer can enable an option to run this verification every time they do a decompile to add a little bit more correctness guarantee to their decompilation process. And before I introduce our algorithm, our semantics, it's important to understand what are the current techniques used in control flow restructuring. So here is a particular control flow diagram. It has 2 states, L and R, and the starting state is the left state. And the left state under condition B will execute P to R, and from R it will exit if condition B also holds, and also in reverse. So this is one way to turn this into a while loop program. Sorry for flushing you with code, but I will explain that. So we introduce a new variable, x, and this is what we call an indicator variable or a dummy variable. And x basically keeps track of which state the current execution is. And x starts with L, and then we iterate through the automata. In these 2 red conditions, it corresponds to transition. As you can see, when the current state is L and B is true, we execute P. And then we set x equal to R to indicate current state is changed to R. And similarly, these 2 conditions represents halting by setting x into halt, and it will exit the loop and terminate. So this is a very naive implementation of the restructuring. In the real world, it's much more sophisticated, but in the real world, they also use indicator variable in similar ways. A perhaps more clever way to reconstruct this is by using the structure of the loop and break out of the loop when necessary. So we can see like there are primarily two ways of doing control flow restructuring. First, they would use break, continue, return, things like that, which we call non-local control flow. Second, they use indicator variables. And another important thing to realize is that the correctness conditions are almost always guaranteed by trace equivalence, in the sense that under the same condition, they will execute the same command for both programs. And whenever you see trace equivalence, you should think clean algebra. If I ever start a cult, I would let all my cultists to say clean algebra every time people mention trace equivalence, because starting a cult is fun. And in particular, we choose guarded clean algebra with test, which is a variant of clean algebra with test. And the reason is that it's very fast to validate equivalence within guarded clean algebra with test. However, guarded clean algebra with test is very bearable. This means that it has no support for indicator variable. It has no support for non-local control flow. Well, what do? We just add it, right? This is not the first time we extended clean algebra. What can go wrong? So the syntax is rather simple. We have the theory of guarded clean algebra with test providing us with if statement sequencing while loops, the normal while program. And we add indicator variable or dummy variable. They basically only can be assigned from a finite set of constant value. So you cannot do x equals to x plus 1, and they can only be tested against the current value of x. And we also add non-local control flow, which includes break, return, and in particular, we also include label and goto. The reason is, in order to prove the control flow restructuring is correct, we actually need to compare the program pre-restructuring and post-restructuring. And the program pre-restructuring are control flow graphs, which are typically represented as goto program. So goto and label are very essential in this system. So now we encounter our first problem. We realize that the trace semantics cannot record the indicator value. Why? Because if we look at the original program that we have using indicator value to do the control flow restructuring, comparing it with the goto version of the program, which represents the control flow graph, one of them has the indicator variable in there, but the other one doesn't. This means that if we record the indicator, the value of the indicator variable, these two can never be equal, right? However, if we don't record indicator variable, it causes problem in composition. If we want to define our semantics inductively, we necessarily need to, when we compute the composition, we necessarily need to compute the first and then compute the semantics of the second. And notice the first cannot record the value of x, but the second needs to depend on the value of x. So this doesn't work. Another challenge is non-locality. For example, what should the semantics of break be? In a normal program, we all know what the semantics of break is. Break will simply exit the loop and execute Q in this case. But to define the semantics inductively, we necessarily need to consider the semantics of break in a vacuum, which is very confusing. Similarly, it's also very confusing to think of the semantics of goto, because we don't really know what goto will do until we know what label L will do. Turns out both of these problems can be solved by introducing an intermediate semantics, which we call continuation semantics. Continuation semantics does two things. It records the ending indicator value. For example, in here, the semantics of x equals to 1 under the starting starting indicator value I, it will say under any condition, which we represent using alpha, it will halt and output indicator value 1. And by halt, we denote halt by accept. And similarly, for non-local control flow, a go to L will simply be resolved into a continuation jump, which says under any condition, we will jump to label L and starting with I. So notice that the jump here is merely syntax. It doesn't have any semantical meaning, and we will resolve the semantical meaning later. And then we can obtain our trace semantics, or we call guarded language semantics, from the continuation semantics. In the indicator value case, we simply remove the ending indicator. We no longer needed it because we have already computed the semantics of the entire program. We no longer need to compose anymore. And for the semantics of go to L, we will resolve all the jump continuation by replacing it with the semantics that computed starting from label L. So by introducing the continuation semantics, it kind of gives us a breathing room so that continuation semantics can be defined inductively, and then we can lower it into the guarded string semantics, which is the actual trace semantics that we want. Okay, so that's the denotational semantics. What is the operational semantics? We first introduce an operational model, which we call CFG cat automata, which is very similar to control flow graph that I have demonstrated before, or GCAT automata, which is basically the same as control flow graph. So you notice instead of, when transitioning from states to states, instead of saying, oh, under condition B, I will execute P, I also record the starting and ending indicator value because they are important. And from a state, under a condition, instead of just halting, it can also output a continuation like jump. And for each label, we have a special state to represent the entry point to tell the automata how to enter from that particular label. In this case, you can only enter the automata when you start from indicator value 3 and condition C holds. Then you will execute Q and you end up with indicator value 5. And if we simply trace all the commands and the conditions that the CFG-CAT automata has, we can get the continuation semantics from there. And similarly, like lowering continuation semantics into guarded language semantics, we can also lower CFG-CAT automata into GCAT automata, simply by pushing the indicator value into states so that we are no longer tracing the indicator value. They are part of the state now. And we are connecting all the jump with their corresponding entry point. And this is the result from the original GCAT paper. If you trace the condition and action of GCAT automata, you get a guarded language semantics. And we proved that this square commute in the sense that if you compute the semantics first and then lower, it's exactly the same as lower first and then compute the semantics. So this is a very nice correspondence we get. So at this point, we have the domain of the operational semantics. We actually need to define the operational semantics. That is, how does for each expression or program, we need to give a certain automata in the domain. And this is through Thompson's construction, which is very similar to the original Thompson's construction proposed for GCAT. And finally, we proved the correctness of this Thompson's construction by showing that the continuation semantics of the CFG-CAT program and the CFG-CAT automata coincide. That is, this triangle commutes. If we compose it with the previous commuting square, we get a very nice picture. You might not believe me, but I will show it. If you go from the top, this is basically doing like operationally. So you compute the operational model, you lower the operational model, and then you trace the operational model. So this gives you the operational semantics. This gives you a semantics to compute operationally. And if you go down, it gives you a semantics to compute denotationally. And this, the commuting of these two, this triangle and this square means that the operational semantics and the denotational semantics of our program coincide. So that's a very nice property. But beyond that, it's even nicer because in the original GCAT paper, they proved that guarded language semantics has a very strong correspondence with GCAT automata. Specifically, for any two GCAT automata, they have the same semantics if and only if they are bisimilar. So this gives us a way to construct a correct algorithm. For example, if we given two CFGCAT program, we can simply compute their automata using Thompson's construction and then lower it into GCAT automata, and we run bisimulation, then we obtain their equivalence. And because of the correctness of GCAT automata, we get our correctness for CFGCAT program, that is, decision procedure will return true if and only if input programs are trace equivalent. So we produce no false positive and no false negative with respect to trace equivalence. And finally, the conclusion is that we give intermediate semantics, we give operational semantics, respectively using continuation semantics and CFGCAT automata. And we prove the equivalence between our operational and denotational semantics. And we give a correct decision algorithm. And finally, we implemented we constructed a prototype implementation. We send some particularly nasty function in core util into there. There are nested loops, there are gotos in the original program, and when we compile and decompile that program, we can barely recognize it from the original program. They added like 3 more gotos in the original program, and turns out if we run our validator on it, it can validate it in like half a second. So our implementation is pretty good. So some future work. Our implementation is pretty good, but it can be improved. We can use some symbolic algorithm to speed up the implementation. And we can integrate with existing compilers so people can actually use it. And we are also working on equational axiomatization. It's pretty hard, but I think I have an idea how to do it. But I said it about my previous 5 attempts, so I don't know. And we are trying to do a graphical axiomatization. It's because in a lot of these algorithms, they actually do graph algorithms on the control flow graph. So for example, they are finding cycles with the control flow graph. They're saying if there's an exit of the cycle, then do this. So it seems like a graphical axiomatization, a graphical proof theory, it's kind of necessary in this domain. And for current progress, I made some friends with string diagram people. And just as a proof, we all love proofs. This is Wojtek Rozowski, and this is Leo Lobowski. And I didn't have time to take a selfie with Rolf Sarsky, and he sent me this. And I didn't have time to add myself in there, but just to tell you, I actually have friends. And questions? Hi.
Okay, thank you for great talk. So I think we can take only 1 or 2 questions first.
Nice talk. So since you're showing Wojtek and Ralph.
Sorry, you can give me a microphone.
Since you're already showing.
You're turning down.
Yeah. Since you're showing these guys who are working on probabilistic systems, so do you know or think that your full abstraction result would apply to probabilistic linear algebra as well?
Yeah, so guarded linear algebra with tests has a probabilistic model. But I don't see like probability used in very non-trivial way in the decompilation algorithm. So I don't know if we have a dedicated probabilistic system for it. But I think our system can verify probabilistic systems. So it's within the semantics. Yeah.
Okay, so any more questions? Okay, so if you have no questions, I have one.
Oh, please. Okay.
So I want to know, so I know we can remove the continue and break without counter semantic. So why do you include them in your semantic? And also, since we are going to model the value of variables, have you considered using epsilon interpretation?
Sorry, can you reiterate about continue and break?
So I know that we can remove that without harming the program semantic. That's just semantic sugars, right?
Oh, no. Oh, yeah, right. So the reason we include these kind of non-local control flow instead of doing everything using goto is because that's what we are actually verifying, right?
Yeah.
So we are verifying that control flow transformations, which means that, say, if you replace a loop with goto, it's actually correct. So, and if we have this kind of goals, replacing everything with goto seems like counterproductive. That's the reason.
Okay.
Does that make sense?
Okay.
Yeah.
Thank you for
And
answering.
we haven't done abstract interpretation. Sorry.
Okay. Okay. Thank you for answering. So let's thank Chen again for his great talk. Where's Tobias? Oh yeah. Okay, so when he is preparing, let's introduce him. So let's welcome the next speaker, Tobias, and he's introducing the algebras for deterministic computation and as inherently incomplete. Okay.
All right, does this work? Yeah. Oh, I have to unlock my screen. There we go. And maybe if I... All right, just a second, please. All right, hi folks. Thanks for sticking around for the last set of talks. Yeah, I'm Tobias, and I'm presenting joint work with Balder ten Kate, who's based at the University of Amsterdam. So let's get right into it. When people program, they have to concern themselves with flow control, right? So which things happen, and in what order, and under which conditions. And there are many ways to express this. For instance, you could draw a flowchart. But flowcharts can get very big and very complicated and hard to read. So what we really do is we tend to express these things using code. Now, this is all well and good. But sometimes this intuition that, you know, if I have a flowchart, then I can render it in code breaks down. As an example, let's consider this flowchart right here. And I think it helps to go over the details. So what you have here is, let me indicate it here. We have a program that starts, and it checks whether a condition A is true, right? And if it's not true, then the program stops. But if it is true, then we will execute some. And then we'll check again. And if it's still true, then we stop the program. But if it's not, then we run X again, and then we start over. And you can look at this for a while, and you can scratch your head. And eventually, you'll probably conclusion that this program can be informally described as follows. If A is true, then repeat X while A is changing, right? So if A has the same value after executing X as it had before, then we stop the program. And rendering this in code can be quite a puzzle. One way to go about it is, and this is actually corresponding to one of the automata that Chung showed you a moment ago, is you can use a loop with a break statement. And this kind of reveals why it's hard to render this in code, because here you have a loop that goes back and forth, but there's no clear exit condition on the loop, right? On the left, we exit if A is false, while on the right, we exit if A is true. But here we have a while loop, and we can end it prematurely in the middle by using a break statement. Another way of doing it is by introducing an extra variable to keep track of where we are in the flowchart. And you've also seen an example of this in the previous talk. And you can also just throw up your hands and say, I don't know, but I can use gotos. So this is also a valid implementation of this, this flowchart. And finally, and I did not put this on the slide, but of course you can also use like till recursion to implement this program. So these are all code renditions of this flowchart, but they all have, well, let's say, slightly objectionable features. On the one hand, the two programs that have break and return have non-local flow control, right? Which makes them hard to validate and to analyze. And this program with the flag, well, it introduces something that was not part of the original flowchart. All of a sudden, there's this variable hanging around, and we're, yeah, not quite sure where that came from. And so you might ask yourself, do we need these things, right? Do we need these extra features to implement this seemingly simple flowchart? And the answer is yes. And examples of cases like this have been known since the 70s, of flowcharts that can be hard to implement using traditional code and where you need these non-local flow control features. So if having just if, then else, and while is not enough, what do we need to express everything? And there's a range of options that we can go with. So we just seen the break statement. And it turns out that having a single level break statement gives you more expressivity. For instance, you can express the flowchart that we saw before. But even then, there are things that you cannot express. If you have multi-level break statements, which some languages do have, then you can express everything. And having variables also always lets you like sort of simulate the flowchart, right? Like you keep a variable, where are we in the flowchart? So you basically implement that. There we go. No worries. All right, check, check. Great. But as I said, these features in programming, I mean, they can be quite, well, they can make your program harder to analyze, right? Having break obscures your loop condition. It's no longer clear when your loop is terminating. Having multi-level break makes this problem even worse, and there are very few languages. Can I use this? All right. All right, so, and using variables to make your flow control explicit, or well, make it implicit by putting it in the data flow can make your code harder to read as well. And non-trivial till recursion is also not ideal always. And that's before we even start to think about giving a semantics to languages that have these features, right? If you try doing that, then, well, you might end up looking like that. So we asked, are there local control flow primitives that can express all deterministic control flow? So for example, maybe there was something that we were missing, right, in our original tool set. Maybe if we just have if then else and while, but also the repeat while changes program that we saw before, maybe then we can express everything. Who knows? Unfortunately, as you might be able to tell from the title, the answer is no. And there's a little caveat, which is that if you allow yourself to have infinitely many primitives, then yes, you can express everything. But let's not go there. So how do we prove this? How do we formalize this? We turn to Kleene algebra with tests. And if you don't yet know what that is, don't panic. Basically, it's a way of expressing the kinds of behavior that your program can express using what are more or less regular expressions, right? Like you write a regular expression for the types of things, for the patterns of behavior that your program can do. And you can put little Boolean assertions inside to annotate under which conditions these things are executed. So as an example, I can have if then else, the traditional if then else like this. And I can write a cat expression for it that looks like this, where there are two non-deterministic branches. In the left non-deterministic branch, I check whether B is true and then run E. Whereas in the right non-deterministic branch, I check whether B is false and then run F. Now this program has non-determinism, but it's still is deterministic because only one of these two branches survives, right? B is either false or true. And here, we can simulate a while loop using cat by writing this cat expression, which says, run the body of the loop some number of times, and each time the condition is true, and finally, when you're done, the condition is false. So this also describes the pattern of behavior that you would see using a while loop. Now, cat comes equipped with a relational semantics, and the way this works is you take a predicate for every test letter, and you take a relation on your state space for every action, and that'll give you a way of moving from cat expressions to relations on your state space. And because this is POPL, I think I can get away with writing this as a dependent type. Now, because, as I said, cat expressions are basically glorified regular expressions, that means you can model them using finite automata, and you've seen these also in the previous talk. And there's so the way you read these automata is you have transitions that have two things on them. This says you can take this transition if T1 is true, and this says when you take this transition, execute the action P1. And here we have these double arrows that say when a state can accept. So this state can accept if both T1 and T2 are false. And again, because we're doing this in a regular setting, these automata have a close one-to-one correspondence with expressions. So everything you can write using a cat expression, you can also do using an automaton, and vice versa. It's basically a version of Kleini's theorem. But remember, we were interested in deterministic control flow, right? So, and I said that cat expressions can have non-determinism because of the plus inside. So how do we select the expressions that are deterministic? It turns out there are two ways of doing that, and they are equivalent, fortunately. So one way is to say, okay, take the semantics of your expression. You can supply it with an interpretation of your primitive letters. And if you give it an interpretation that assigns a partial function to every letter, not just a relation, but a partial function, and you get out a partial function always, then we call that expression deterministic. But equivalently, you can say your expression is deterministic if its automaton is. And these are the same thing. So this is a robust notion within the theory that we're working in. So we've already seen some deterministic expressions, right? I already explained that this one is deterministic because only one branch survives. And by similar arguments, you can show that there's no non-determinism here either, because either you continue with your loop or you halt. So let's put this theory to work. Here's an automaton for the expression or the idea that we saw before, which is that we need to repeat some program P while some test T is changing. You can think of this as a flowchart, but as an automaton, it looks like this. And because of the correspondence between automata and expressions, you can also render this as an expression, and then you get this little monster right here. And this is also a deterministic expression because it comes from a deterministic automaton. So now we have a new primitive for flow control, in addition to the if, then, else, and while that we saw before. So we can just write this as a, well, direly needed shorthand for this right here. And now we can formally state the thing that we observed before, which is that if you build expressions using if, then, else, while, and sequential composition, then you cannot build any expression E, right, that is equivalent to this repeat while changes program. And again, referring to old work from the 70s of people that were already aware of this, but they weren't using cat. So, all right, so these are known results, but where are we? Basically what we did is we developed this hierarchy of different kinds of expressivity. At the very top, we have cat, and we feel like this is a reasonable ceiling because here you can write everything that you can write using an automaton, or equivalently anything you can write using a flowchart. So basically anything you can dream of. And within this, we have the deterministic cat expressions. And inside that, there are the expressions that you can build using sequential composition, if, then, else, and while. All right. And I just argued that if you add the repeat while changes thing as a primitive, then you get a slightly larger set of behaviors that you can express. And on top of that, so what we actually showed is that even outside this blue zone, right, there's another fragment where there's some other spooky operator that you can add that is more expressive than the blue circle, but less expressive than the stuff in the green circle. And this goes on infinitely. So even beyond this, there's another fragment of deterministic cat that cannot express everything, but is more expressive than this. And you can just keep doing this. So this implies a hierarchy in terms of what can be expressed. So formally, what we showed is that for every deterministic fragment of cat generated by finitely many operators, there exists an additional cat expression that cannot be expressed using those operators. In what little time I have left, I can try and give you an idea of the proof. If you want the full gory details, then I'm going to refer you to the paper. So here's the idea. If you have an expression, for instance, the one for sequential composition, you can turn that into an automaton. And in case of sequential composition, the automaton looks like this, right? You first unconditionally run P1, then you unconditionally run P2, and then you unconditionally accept. Fine. You can also have if then else, and the automaton looks like this. So here, if T is true, then you run P1, you go to Q1. If T is false, you run P2, you go to Q2. In both cases, you're done. And you can also have an automaton for while. And the automaton looks like this. You have one state, you loop while T is true, and you run P, and otherwise, if T is false, then you accept, then you're done. Now, if you look at this automaton, it has a sort of behavior that, wait, let me take a step back. Composing these expressions, right, means that you're also kind of composing these automata. So we have a way of making that clearer formally. And it turns out that if you compose automata like this, you will never be able to build an automaton like this, where there's two states jumping back and forth, but they have possibly contradictory ending conditions. But now if you add this automaton, which corresponds, well, it's not quite, but it's very close to the repeat while changes program, right? If you add that to your set of expressions that you can use to build more flow control, then there's another automaton, which is kind of a generalization of this two-state automaton that you cannot express. And this goes on, right? There's even a four-state version of this one, so there's an infinite family of things that you're going to need to add to express everything. So that concludes the technical part. So these automata satisfy a property that we call them all one dense. And this automaton right here we call two dense, and this is three dense. And what exactly that means is, well, I'm not going to tell you, but it comes down to how connected the automaton is, how clique-like it can be. And so all of the automata that you built using the traditional flow control operators are one dense. And our question is, does this characterize all of the automata that you can build using GCAT? We don't know. And we don't have a very good handle on it right now. Also, we wonder if this result is still true for extensions of CAT. So there's some buzz around Kleene algebra with tests in domain lately. You can also look at Kleene algebra with tests in intersection. And I mentioned a result, well, I obliquely mentioned a result by Kosoraju earlier, which implies a sort of hierarchy in terms of what you can express if you have multi-level breaks, right? If you have single-level break, you can express more than not having it. If you have two-level break, you can express more, etc. So how does our hierarchy compare to Kosoraju's? And finally, we wonder if there's a different kind of composition that can incorporate maybe n-level breaks. So perhaps algebraic effects. That's all I have for you today. Happy to answer your questions.
So, okay, so let's thank for great talk. We can take one or two questions.
Question. Could you give some intuition of what kind of control flows are non-local? Like there are some examples, but is there some general criteria to determine which is non-local?
Yeah.
So I don't have a very crisp definition for you, I'm sorry. It's just anything that uses break or go to, I'm calling non-local.
Okay, sounds good.
Yes. In contrast, so I guess non-local is the bad thing. The good thing is something algebraic, right? Where you can have, where you can compute the semantics of it by computing the semantics of its operands and then putting those together. So if then else, right, you can compute the semantics of the if, so the if branch and the else branch, and then compose those. And that's what we want.
While it's also local for that reason.
Yes. Yeah.
Okay, so thank you for the question. Yeah.
Thank you for the talk. I have a slightly high-level kind of question. What do you think about adding key parameterized operator that can cover any n-dense thing? Yeah.
So in our paper, we eventually have, like, towards the end, we have a positive result, which does something like you're proposing. So basically, we introduce a kind of parameterized or an infinite family of operators that kind of corresponds, is kind of a template for like n-wise tail calls that you can use. So I think that sort of covers where you were going, right? Yeah.
Okay, so any more questions? Okay, let's thank Tobias again for his great talks.